The landscape remembers what history has forgotten. Beneath modern towns lie older streets. Beyond ruined walls, stairways descend into chambers sealed for centuries. On distant hills and isolated cliffs, monuments still mark places whose original meaning has faded almost completely. These structures once belonged to living worlds filled with people, rituals, beliefs, and knowledge, but only fragments of those worlds survived. Archaeologists can recover inscriptions, tools, foundations, and buried rooms, yet some discoveries only make the story more difficult to reconstruct. The ancient past is not a single mystery waiting for one answer, but a vast collection of unfinished stories scattered across the earth. Today, we travel to the places where those stories still remain written in stone. Far beyond the crowded temples of Luxor, hidden beneath the burning limestone cliffs west of the Nile, lies a necropolis where some colours have survived longer than entire civilizations. Inside the Valley of the Queens, paintings more than 3,000 years old still glow with the deep blues, blood reds, and gold tones so vivid they appear almost modern. Archaeologists expected faded dust. Instead, they found walls that looked freshly painted. The deeper researchers looked, the stranger the sight became. The valley was officially explored in the early 19th century by European expeditions, but systematic excavation accelerated after the work of Ernesto Schiaparelli in 1904, when the tomb of Queen Nefertari was uncovered. Buried beneath debris and sealed chambers, the tomb revealed some of the finest surviving art in ancient Egypt. What shocked researchers was not only the beauty of the paintings, but their impossible preservation. The greatest mystery of the Valley of the Queens is not gold, mummies, or curses, it is chemistry. In the tomb of Queen Nefertari, many pigments remain astonishingly vibrant after more than 30 centuries. Modern conservation teams discovered that the walls were built in multiple engineered layers: limestone bedrock, mud plaster, fine gypsum coating, mineral pigments, and an ultra-thin protective organic layer. The structure functioned almost like a sealed laboratory environment. The famous Egyptian blue pigment remains one of the oldest synthetic pigments ever created by humans. To produce it, ancient craftsmen had to heat silica, copper compounds, calcium, and alkali materials to temperatures between 850 and 1000 degrees Celsius. That level of thermal control rivals early industrial ceramic production. Even more mysterious, modern infrared imaging revealed that Egyptian blue emits luminescence under infrared light, a property unknown to science until recent centuries. Compared with Roman frescoes in Pompeii, many of which faded or deteriorated after volcanic exposure, or medieval pigments that darkened within a few hundred years, the Valley of the Queens demonstrates chemical stability that seems centuries ahead of its era. Scientists studying the tombs also discovered that the walls absorb and release moisture extremely slowly. Salt crystallization, one of the greatest enemies of ancient art, was minimized because the tombs maintained unusually stable humidity levels. Some researchers now believe the Egyptians intentionally selected certain plaster mixtures to regulate microscopic water movement inside the walls. The mystery becomes even deeper when examining restoration damage. After the tomb of Nefertari was opened to tourism in the 20th century, rising humidity from visitors immediately began degrading the paintings. Carbon dioxide, sweat moisture, and airborne fungi started damaging surfaces that had remained stable for over 3,000 years. This revealed a disturbing truth. The tombs may have originally been engineered as perfectly balanced microclimate chambers. No one fully understands how ancient Egyptian builders achieved such environmental precision without modern chemistry, climate science, or laboratory instruments. The Valley of the Queens was carved directly into unstable limestone cliffs near ancient Thebes. Geological surveys show that many sections of the rock contain natural fractures capable of causing collapses. Yet, numerous chambers survived thousands of years with minimal structural failure. Ancient engineers appear to understand stress distribution inside the mountain. Several chambers feature subtly curved ceilings that function similarly to load-dispersing vaults in later Roman and Gothic architecture. In some areas, workers intentionally left stone pillars untouched, creating primitive load-bearing support systems. The precision is difficult to explain. Many corridors maintain remarkably straight cuts over long underground distances despite supposedly being excavated with copper chisels and dolerite-pounding stones. Some wall surfaces are so smooth that modern archaeologists originally assumed later restoration work had modified them. Researchers also identified narrow ventilation shafts and secondary pits that may have reduced heat buildup and dust during excavation. Mining engineers have compared these systems to early underground airflow management techniques. For a civilization working in darkness with oil lamps, primitive tools, and no modern surveying equipment, the consistency of these underground structures remains deeply puzzling. Several tomb ceilings inside the Valley of the Queens contain detailed celestial imagery representing the Egyptian afterlife. But these were not simple decorations. The stars painted across the ceilings may correspond to real astronomical cycles, particularly Sirius, whose heliacal rising mark the annual Nile flood. Some Egyptologists believe the ceilings encoded calendrical information tied to agricultural cycles and religious ceremonies. The precision of certain star arrangements has generated debate for decades. Ancient Egyptians may have observed the sky continuously over centuries to maintain long-term astronomical records. What fascinates modern lighting specialists is the visual effect inside the tombs. Under weak torchlight, the deep blue pigments absorb light differently from surrounding mineral paints, causing stars to appear unusually vivid in darkness. Some researchers compare the effect to primitive immersive environmental design. In a sealed underground chamber illuminated only by flickering firelight, the ceilings may have appeared almost alive. Unlike the popular image of obvious pyramid entrances, many tombs in the Valley of the Queens were deliberately disguised. Entrances were concealed beneath rubble, plaster coatings, and natural-looking rock debris. After only a few years of desert erosion, distinguishing a tomb entrance from the surrounding cliff became nearly impossible. Some chambers include misleading side corridors, blocked passages, and concealed niches that may have confused tomb robbers. Archaeologists also found evidence that certain tombs were reopened centuries later by Egyptian officials themselves for repairs or ritual reuse. This raises a difficult question. How did they relocate hidden entrances after the landscape had naturally changed? Several historians believe the valley functioned as a controlled security complex rather than merely a burial ground. Compared with many royal tombs that were looted within generations, some chambers in the Valley of the Queens remained hidden for extraordinarily long periods. One of the least understood mysteries is the environmental stability inside the tombs. Deep chambers experience very small temperature fluctuations compared to the outside desert, where daytime temperatures can exceed 40 degrees Celsius. The surrounding limestone acts as a massive thermal buffer, absorbing heat slowly and releasing it gradually. Modern monitoring revealed that even slight increases in visitor numbers dramatically alter humidity and carbon dioxide levels. In some areas, fungal colonies began appearing only decades after the tombs were reopened. This suggests the original environment existed in an extremely delicate equilibrium for thousands of years. Scientists now compare certain chambers to sealed archival vaults designed for long-term preservation. Yet these chambers were built over 3,000 years ago, with no electricity, no climate control systems, and no modern understanding of microbiology. The longer researchers study the valley, the more it appears that ancient Egyptian builders possessed an environmental awareness far beyond what historians once believed possible. Near the Valley of the Queens stood the workers' village of Deir el-Medina, where archaeological records revealed organized labor shifts, material management, payment systems, and strict progress tracking. This looked less like chaotic slave labor and more like a highly coordinated engineering project. Thousands of square meters of paintings, carvings, and plasterwork inside the tombs may have been completed within only a few years, requiring precise coordination between stonecutters, pigment makers, artists, and priests. Do you think the ancient Egyptian possessed engineering knowledge far beyond what modern historians currently accept? Share your thoughts in the comments below. Perched on a rocky hill west of Isfahan, the fire temple of Isfahan has survived nearly 2 millennia, using little more than clay, mud brick, and dried reeds. In a region where summer temperatures regularly exceed 40 degrees Celsius and powerful desert winds erode exposed structures year after year, the temple should have collapsed centuries ago. Instead, parts of its core still stand above the valley, overlooking the Zayandirud plain like the remains of a forgotten engineering experiment. What makes the site disturbing to archaeologists is not simply its age, but the possibility that ancient builders understood material science, airflow control, seismic resistance, and environmental engineering far better than historians once believed. The structure, often called a Tashka-e-Isfahan, is generally linked to the Sasanian Empire between the 3rd and 7th centuries CE. Yet some researchers suspect the hill itself may have been sacred long before the Sasanians arrived. The complex sits roughly 200 meters above the surrounding terrain, giving a panoramic view across the plains surrounding Isfahan. From the summit, fires lit at night could potentially be seen from enormous distances. That single detail triggered decades of debate over whether the temple served not only religious functions, but also military communication purposes similar to beacon systems used later by the Byzantines and along sections of the Great Wall of China. The modern rediscovery of the site happened gradually through 19th and early 20th century surveys conducted by European travelers and Iranian archaeologists studying pre-Islamic architecture. Early investigators were shocked by the survival of large structural sections because the temple was built primarily from sun-dried mud brick, reinforced with organic material. Normally, mud brick exposed to centuries of rain, thermal expansion, earthquakes, and wind erosion deteriorates rapidly. In Mesopotamia, for example, many mud brick structures survive only as low mounds after a few hundred years unless continuously restored. Yet the fire temple of Isfahan retained standing walls and vaulted sections despite sitting fully exposed on a hilltop. The greatest mystery surrounding the temple involves the strange durability of its clay and reed construction system. Analysis of surviving fragments suggests builders mixed clay with straw or reed fibers before shaping bricks and mortar. Modern engineers comparing the material to reinforced composites discovered something remarkable. Organic fibers distribute stress through the structure in ways surprisingly similar to fiber-reinforced concrete used today. When microscopic cracks begin forming, the fibers slow crack propagation and reduce catastrophic failure. In modern earthquake engineering, similar principles are used in engineered cement composites designed to flex instead of shattering. This becomes even stranger when considering the environment of central Iran. Temperatures in Isfahan can fluctuate dramatically between day and night. Thermal expansion normally destroys brittle materials over long periods. Ancient stone monuments in arid regions often fracture because repeated heating and cooling slowly separates mineral layers. But clay mixed with organic fibers behaves differently. Instead of resisting stress rigidly like stone, It flexes slightly and disperses energy across the structure. Some preservation specialists believe this may explain why portions of the temple survived repeated seismic activity in a tectonically active region. Iran experiences frequent earthquakes due to the collision between the Arabian and Eurasian tectonic plates. Many later stone and masonry structures across the region collapsed entirely over centuries, yet parts of the fire temple endured. That has led some structural historians to propose the temple accidentally incorporated primitive anti-seismic architecture. The lightweight composition reduced gravitational stress, while flexible mud and fiber walls absorbed vibration better than rigid stone blocks. Modern earthquake-resistant buildings sometimes use flexible joints or energy-dissipating materials based on similar concepts. The geometry of the structure adds another layer to the mystery. The temple contains examples of the famous Chahatak design, a four-arch domed arrangement strongly associated with Zoroastrian fire temples. At first glance, the design appears purely ceremonial, but airflow studies on surviving Sasanian structures show the configuration creates highly effective natural ventilation. Hot air rises through the dome while cooler air enters through lower openings, producing continuous circulation without mechanical assistance. For a religion centered around maintaining a sacred flame, this may have been critically important. Fire requires stable oxygen flow but must also be protected from sudden gusts that could extinguish it. Some historians argue the architecture effectively created a passive airflow regulation system centuries before formal understanding of aerodynamics existed. In modern, sustainable architecture, nearly identical airflow principles are used in passive cooling towers and zero-energy ventilation systems across hot climates. Another unresolved puzzle involves the temple's elevated position. The hilltop location provided visibility across the region, but constructing there created major engineering difficulties. Transporting building materials uphill without modern machinery would have required enormous labor coordination. Archaeologists estimate even relatively small Sasanian projects demanded organized workforce logistics comparable to military operations. More importantly, building stable foundations on uneven rock slopes requires understanding drainage and weight distribution. Poorly designed structures on inclined terrain typically collapse as soil shifts beneath them. Yet the fire temple remained standing for centuries. Some researchers suspect the builders intentionally chose lightweight clay composites rather than massive stone specifically because the hilltop terrain could not safely support extreme weight. That decision would indicate practical geotechnical reasoning rather than purely aesthetic or religious choices. Similar logic appears in some ancient Andean civilizations, where lighter, flexible materials were sometimes favored in seismic zones despite the availability of stone. The site's possible military role continues generating controversy. Ruins near the summit include what appears to have been a circular watchtower or beacon platform. If signal fires were lit there, communication across vast distances may have been possible. Ancient empires frequently relied on fire relays to transmit warnings. The Byzantine beacon chain across Anatolia reportedly transmitted messages hundreds of kilometers in a matter of hours. Some historians believe the fire temple may have functioned as part of a similar early warning network protecting central Persia. What makes this theory fascinating is the blending of religious and strategic architecture. In many ancient societies, temples also served political and military functions, because sacred sites were among the most secure and respected structures in the landscape. If the fire temple acted simultaneously as a religious sanctuary, observation platform, and signal station, it would represent an advanced multi-purpose design rarely discussed in mainstream history. The hill itself may also have astronomical significance. Certain researchers argue some structural alignments correspond loosely with solar positions during seasonal transitions important in Zoroastrian ritual calendars. Unlike sensational ancient alien claims, however, evidence remains inconclusive. Still, elevated sacred structures linked to celestial observation appear across numerous civilizations, from Mesopotamian ziggurats to Andean ceremonial platforms. The possibility that the fire temple combined ritual fire worship with observational astronomy remains difficult to dismiss entirely. Perhaps the most overlooked feature of the site is its microclimate behavior. Thick mud brick walls absorb heat during the day and release it slowly at night, stabilizing interior temperatures. Even today, traditional desert architecture across Iran uses similar thermal mass principles to reduce extreme indoor heat without electricity. Measurements in comparable adobe structures show internal temperatures can remain significantly cooler than the surrounding environment during peak daytime heat. In effect, the temple may have functioned as a naturally climate-controlled structure long before modern environmental engineering emerged. Do you think the builders of the Fire Temple of Isfahan truly understood advanced engineering principles far ahead of their time, or are we still underestimating ancient civilizations? Share your thoughts in the comments below. Inside the limestone mountains of Jebel Buhais, archaeologists uncovered a prehistoric cemetery in one of the harshest environments on Earth. Temperatures here can rise above 45 degrees Celsius. Rainfall is extremely limited, and yet thousands of years ago, humans repeatedly returned to this dead landscape to live, travel, bury their dead, and somehow survive. What they left behind would expose one of the strangest ancient survival systems ever discovered in the Arabian Peninsula. The modern discovery of Jebel Buhais began in the 1990s when construction work near the mountains revealed ancient graves hidden beneath layers of desert sediment. Excavations led by teams from the Directorate of Antiquities in Sharjah and German archaeologists soon uncovered hundreds of burials dating from the Stone Age to the Bronze Age, especially between roughly 5000 and 4000 BCE. Human skeletons, tools, ornaments, animal remains, and imported marine materials appeared in a region that today seems almost incapable of supporting permanent life. The deeper researchers dug, the more impossible the site began to look. One of the greatest mysteries surrounding Jebel Buhais is water. Modern survival in this region requires advanced infrastructure, transported supplies, and constant access to groundwater systems. Yet prehistoric communities existed here thousands of years before metal pipelines, wells powered by machinery, or large-scale irrigation. Geological studies show that the mountains contain fractured limestone formations capable of trapping seasonal groundwater deep inside natural cavities. Some researchers believe the inhabitants understood these underground water systems with astonishing precision. Certain ancient camps and burial clusters appear repeatedly near zones where moisture naturally accumulated beneath the rock. This suggests they may have identified invisible groundwater reservoirs simply by observing mineral stains, vegetation patterns, stone temperature, or seasonal humidity changes. Compared to civilizations beside the Nile, Tigris, or Indus rivers, Jebel Buhais had no massive water source sustaining its population. That comparison makes the site even more difficult to explain. Ancient Egypt depended on predictable flooding cycles. Mesopotamian cities developed around irrigation canals. But the people of Jebel Buhais operated in a landscape where a failed season could mean death. Some archaeologists believe survival here required a mobile migration system synchronized with climate cycles. Isotope analysis of human remains suggests diets combining marine protein with inland desert resources, implying seasonal movement between the coast and the mountains. In other words, these people may have developed a prehistoric environmental algorithm, a survival pattern refined across generations through observation of wind, temperature, and water availability. Another unexplained feature involves the mountain itself. Jebel Buhais is filled with karst formations, caves, and narrow limestone fractures formed over millions of years. Inside some cavities, temperatures remain significantly cooler than the outside desert. Researchers suspect ancient inhabitants intentionally used these natural chambers as primitive climate control systems. Long before mechanical cooling, the mountain may have functioned like a giant passive refrigeration structure. Water stored inside shaded limestone chambers would evaporate more slowly. Organic materials could survive longer. Even the placement of burials appears strangely deliberate. Several graves were positioned where shadows remained longest during the hottest parts of the day, suggesting an advanced understanding of solar movement and thermal behavior. However, the most disturbing mystery at Jebel Buhais is not how the living survived. It is how the dead were preserved. Normally, desert environments destroy organic material rapidly through heat, salt exposure, and shifting soil chemistry. Yet many skeletons discovered at Jebel Buhais remained unusually intact despite being over 6,000 years old. Some retained remarkable structural stability compared to remains from wetter climates of similar age. This shocked researchers because the Arabian Gulf region is not generally considered ideal for long-term bone preservation. Scientists began investigating the chemical composition of the surrounding sediment and limestone. Preliminary studies suggested the mountain created an unusually stable microenvironment. The porous limestone may have absorbed moisture while simultaneously reducing bacterial activity inside certain burial zones. High mineral content in the soil possibly slowed decomposition further, creating conditions similar to a natural dehydration chamber. In simple terms, the mountain itself may have acted like a giant preservation machine. But the mystery goes deeper than natural geology. Several burials appear to have been intentionally placed in position maximizing airflow through rock fractures. Some graves were constructed using stone arrangements that reduced sand accumulation and heat exposure. This has led to speculation that the inhabitants understood preservation processes far better than previously assumed. They may not have practiced embalming like the Egyptians, but they possibly manipulated temperature, airflow, and mineral-rich soil to slow decay naturally. If true, that would represent an extremely advanced empirical knowledge of environmental chemistry long before formal science existed. The preservation becomes even stranger when compared with other prehistoric sites in Arabia. Many ancient skeletons discovered in open desert environments fragment heavily or disappear entirely after millennia. Yet at Jebel Buhais, archaeologists recovered enough intact remains to conduct isotope studies, dental analysis, trauma research, and even migration reconstruction. In some cases, bone density survived well enough to reveal repetitive muscle strain patterns. These analyses showed that many individuals walked enormous distances regularly. Leg and shoulder development indicated constant mobility across difficult terrain, reinforcing theories of seasonal migration routes, stretching between inland mountains and the Gulf Coast. Another unresolved mystery involves trade and navigation. Archaeologists found marine shells and ornamental materials originating far from the mountain region. This means the inhabitants maintained long-distance exchange networks despite living inside an extremely hostile environment. Without advanced roads, pack animals, or written maps, they somehow transported resources across burning desert terrain. Some researchers compare these survival strategies to later Bedouin navigation systems, where travelers memorize star positions, rock formations, and seasonal wind directions. The difference is that Jebel Buhais predates many documented desert navigation traditions by thousands of years. The graves themselves also reveal unusual engineering choices. Stone slabs were often angled in ways that reduced direct wind pressure from desert storms. After thousands of years of erosion, many tomb structures still maintain their original form surprisingly well. This suggests generations of experimentation with local materials and airflow dynamics. Similar passive engineering principles appear in later desert architecture across the Middle East, including wind towers in Persia and heat-resistant stone structures in Nabatean settlements. But Jebel Buhayes may represent a far older prototype of environmental adaptation. One of the most unsettling aspects of the site is its discontinuous occupation history. Archaeological evidence indicates the area was abandoned multiple times before being reused centuries later. Climate records from ancient lake sediments and regional geological data suggest the Arabian Peninsula experienced dramatic environmental fluctuations during the Holocene period. Jebel Buhayes may have functioned as a kind of prehistoric climate refuge, occupied only when rainfall, groundwater levels, and migration conditions aligned correctly. If that theory is accurate, then the people of Jebel Buhayes were not primitive survivors wandering blindly through the desert. They may have possessed and accumulated environmental intelligence capable of tracking climate behavior across generations without written records, satellites, or scientific instruments. They understood when to move, where to find hidden water, how to exploit mountain cooling systems, and possibly even how to preserve the dead using nothing except natural geology. What do you think was the real secret behind the survival system of Jebel Buhayes? Forgotten environmental knowledge, ancient engineering, or something we still completely misunderstand? Let us know your theory in the comments below. Dalton was discovered near the wetlands south of the Black Sea coast in modern-day Bulgaria, roughly 20 kilometers from Burgas. Archaeologists first identified the remains in the late 19th century after local farmers repeatedly uncovered Roman bricks, coins, and buried stone structures beneath marsh-like terrain. Short excavations eventually revealed something unexpected: an advanced Roman colonial city built directly on unstable coastal ground that should have been extremely difficult to engineer nearly 2,000 years ago. Satellite mapping, ground-penetrating radar, and soil analysis later exposed a sophisticated urban grid buried beneath layers of sediment. The deeper researchers excavated, the stranger Dalton became. Beneath what appeared to be an ordinary Roman settlement were engineering solutions that resembled principles used in modern geotechnical construction: hydraulic management, thermal control, and material science. What shocked researchers most was not simply that the city survived, but how well parts of it survived despite humidity, salt exposure, unstable soil, earthquakes, and centuries of abandonment. Dalton was constructed in a low coastal zone filled with clay-rich sediment and wetland deposits. Modern engineers classify this type of terrain as highly unstable because it compresses under heavy weight and shifts with moisture changes. Today, large buildings in similar environments usually require reinforced concrete piles driven deep underground. Yet large portions of Dalton remained structurally stable for nearly 2 millennia. Excavations revealed that Roman builders created layered foundations using crushed stone, ceramic fragments, compacted sand, lime mixtures, and drainage channels. The arrangement strongly resembles modern load distribution systems used in soft soil engineering. Some road sections still maintain surprisingly flat alignment despite centuries of erosion. The most mysterious part involves the binding material itself. Laboratory studies detected silicate reactions similar to hydraulic concrete. Some samples even showed microcrystalline structures that continued strengthening over time when exposed to moisture. A phenomenon also observed in Roman harbour concrete at sites like Portus and Caesarea Maritima. Researchers compared some Dalton mortar samples to modern Portland cement. In certain durability tests involving salt exposure, the ancient material degraded more slowly than expected for structures nearly 2,000 years old. That raises an uncomfortable question. How did Roman engineers understand soil stabilization and long-term chemical curing well enough to build a durable city on marshland without modern geotechnical science? One of Daltum's greatest mysteries is its resistance to moisture and salt corrosion. The city existed near brackish coastal environments where salt crystals slowly destroy masonry from the inside. Modern concrete in marine zones often deteriorates within decades unless heavily reinforced. Yet sections of Daltum's foundations remain chemically bonded after approximately 19 centuries. Microscopic analysis revealed unusual mixtures of lime, volcanic-like ash particles, crushed ceramics, and mineral aggregates. Bulgaria lacks the massive volcanic ash deposits used in famous Roman concrete from Italy, meaning engineers at Daltum may have developed a regional substitute material capable of producing similar hydraulic reactions. Some researchers believe finely crushed ceramics acted as a pozzolanic additive, creating calcium-aluminum silicate hydrates that strengthened the mortar over time. In modern materials science, similar reactions are intentionally engineered to improve resistance against water penetration and cracking. Even more puzzling is the precision of where these stronger mixtures were used. The most chemically resistant mortar consistently appears in high moisture zones and heavy load sections. It almost seems as if Roman engineers understood which structures required specialized formulas depending on environmental stress. That level of adaptive construction suggests experimentation, material testing, and empirical engineering knowledge far beyond the simplistic image often associated with ancient construction. Beneath Daltum lies a hidden hydraulic network that continues to confuse engineers. Archaeologists discovered underground channels, drainage tunnels, and water management systems maintaining extremely subtle gradients across long distances. In some sections, elevation deviation measures only a few centimeters over dozens of meters. Modern surveyors achieve this accuracy using laser instruments and digital leveling equipment. Roman engineers supposedly relied on ropes, rods, and primitive sighting tools. Yet Daltum's drainage system worked efficiently enough to prevent catastrophic flooding in wetland terrain for centuries. Several channels were also designed to reduce water pressure before discharge, limiting erosion around foundations. Similar pressure management principles appear in modern stormwater engineering. Some tunnels even contain curved sections that appear intentionally designed to slow flow velocity. The precision becomes even more mysterious when considering visibility conditions. Many structures were constructed underground or beneath dense urban zones, where direct line-of-sight measurements would have been difficult. Some historians propose that Roman surveyors may have used advanced water reflection leveling methods or optical alignment techniques now poorly documented in surviving texts. Others argue their practical field experience simply exceeded modern assumptions. Either explanation remains extraordinary. Daltum's bricks display another technological anomaly. Thermal analysis suggests many were fired between approximately 850 and 900 degrees Celsius. Maintaining such temperatures consistently inside ancient kilns would have required highly controlled airflow and fuel distribution. Uneven oxygen flow normally creates warping, cracking, or density variation. Yet many Daltum bricks exhibit remarkable uniformity in hardness, shrinkage, and composition. Some kiln remains indicate surprisingly advanced heat circulation patterns. Certain furnace layouts may have recycled thermal energy internally, improving efficiency and stabilizing temperature distribution, a principle used in much later industrial kiln systems. Researchers comparing Daltum bricks with medieval European examples noticed a striking contrast. In some cases, Roman bricks from Daltum demonstrate greater dimensional consistency than materials produced over 1,000 years later. That comparison creates a broader historical mystery. If Roman manufacturing techniques achieved this level of precision, Why were some capabilities seemingly lost during parts of the medieval period? Magnetic surveys and aerial imaging revealed that Dualtum followed an extremely precise urban grid despite being constructed on difficult terrain. Several roads maintain near-perfect parallel orientation across uneven ground. Building alignments also appear carefully standardized according to geometric planning principles. This matters because small directional errors compound over long distances. Even minor inaccuracies during initial layout should have distorted the city grid significantly over time. Instead, Dualtum displays evidence of centralized planning with surprisingly low deviation. Roman surveyors were known to use the groma, a simple alignment tool for establishing straight lines. But some researchers question whether that alone explains Dualtum's precision, especially in unstable wetland conditions. Astronomical alignment may also have played a role. Certain streets correspond closely with solar orientation angles used in Roman colonial planning elsewhere across the empire. Whether symbolic, practical, or both, the geometric consistency suggests highly disciplined measurement systems. The mystery is not merely that the Romans built accurately, it is that they maintained such accuracy while working in terrain that should have shifted constantly beneath them. Dualtum also contained Roman hypocaust heating systems, networks of hollow spaces beneath floors used to circulate hot air. But the systems here appear unusually efficient. Archaeological reconstructions suggest airflow distribution produced more even heating than many comparable Roman sites. Certain room layouts enhanced natural convection, allowing warm air to circulate through walls and floors with minimal fuel waste. Modern engineers studying the remains noted similarities to passive thermal regulation principles used in sustainable architecture today. Some rooms may even have been designed to maintain different temperature zones depending on social function. If correct, this implies sophisticated understanding of airflow dynamics and heat transfer centuries before formal thermodynamics existed. The deeper researchers investigate Dualtum, the harder it becomes to dismiss Roman engineering as merely primitive ancient construction. Inside the mountains of northern Lebanon, Kadisha Valley cuts through the earth like a wound more than 1,000 meters deep. Entire monasteries hang from vertical cliffs. Ancient stairways disappear into caves. Water systems still function after centuries of earthquakes, floods, and collapse. Even today, parts of the valley remain almost unreachable without climbing equipment. Yet, for over 1,000 years, people lived here permanently, inside stone walls carved directly into the mountain itself. Although local communities knew the valley for centuries, systematic archaeological study only accelerated during the 19th and 20th centuries as European explorers, Maronite historians, and later Lebanese archaeologists began mapping its monasteries and cave systems. Many structures were discovered not through excavation, but because entire cliff sections collapsed during storms and exposed hidden chambers inside the rock. Some caves were so inaccessible that researchers initially believed they were natural formations rather than human-engineered spaces. The first mystery is simple. How are these structures built at all? Kadisha Valley contains monasteries such as Kanubin, Maralesha, and Deir Kushaya, many of them positioned hundreds of meters above the valley floor on nearly vertical limestone walls. Even modern engineers acknowledge that transporting timber, water, lime mortar, tools, and stone blocks into these locations would be extraordinarily difficult without cranes or mechanized lifting systems. Some staircases carved into the cliff are less than 1 meter wide and follow gradients approaching 60 degrees. Yet these routes were once used continuously by monks carrying supplies. Archaeologists studying tool marks noticed that several stair systems display surprisingly consistent cutting depth and spacing, suggesting planned measurement methods rather than random carving. The problem becomes even stranger when compared to other ancient mountain settlements. Sites like Meteora in Greece used rope systems and removal ladders. while the cave cities of Cappadocia relied heavily on soft volcanic tuff that could be excavated relatively easily. Qadisha, however, sits inside harder limestone formations vulnerable to cracking and collapse. Creating large chambers inside these cliffs without triggering landslides would have required remarkable understanding of load distribution and fracture behavior. Several chambers also appear deliberately positioned beneath natural stone overhangs that reduce rainfall erosion. Modern geological surveys suggest some builders intentionally selected rock layers with lower fracture density, something difficult to identify without practical geological experience. Qadisha was not simply a religious retreat, it was a long-term survival system. Temperatures in the valley can fluctuate dramatically between summer and winter, yet some cave rooms maintain relatively stable internal temperatures year-round. Researchers believe the monks exploited the thermal inertia of limestone combined with narrow ventilation shafts to regulate airflow naturally. This resembles passive cooling systems later seen in Persian wind catchers and underground desert structures. Certain chambers contain narrow upper openings aligned with prevailing wind directions, creating convection currents that slowly remove warm air while preserving cooler air below. In modern environmental engineering, similar airflow principles are used in passive ventilation architecture to reduce energy consumption. Water management was equally advanced. The valley receives seasonal rainfall and flash floods, but many reservoirs and channels remained operational for centuries. Some cisterns were carved directly into bedrock and coated with waterproof mortar layers that still retain water today. One of the greatest mysteries is how these builders located reliable underground seepage points without modern hydrogeology. In several monasteries, channels intercept tiny natural water fractures in the rock with remarkable precision. A deviation of only a few centimeters would have caused total failure. Compared to many medieval European monasteries dependent on nearby rivers, Qadisha's systems functioned more like decentralized mountain engineering networks designed for isolation and siege survival. Among all the mysteries in Qadisha Valley, the Byzantine frescoes may be the most difficult to explain. Inside dark cliffside chapels, fragments of red, blue, black, and gold pigment still survive despite centuries of humidity, freezing winters, earthquakes, smoke exposure, and water infiltration. Some paintings date back nearly 800 years, yet sections remain surprisingly vivid. Scientific analysis of pigments in several Lebanese Byzantine sites suggests the use of mineral-based compounds containing iron oxides, copper derivatives, carbon blacks, and imported minerals uncommon to the region. Certain blue pigments may have originated from trade routes connected to Anatolia or even farther east. For isolated monastic communities living inside dangerous mountain terrain, access to such materials implies trade and logistical systems far more sophisticated than previously assumed. The true mystery, however, lies beneath the paint itself. The plaster layers used under some frescoes demonstrate exceptional adhesion to damp limestone walls. In many ancient structures, moisture slowly separates plaster from stone over centuries. Yet parts of the Qadisha frescoes remain tightly bonded even after repeated seismic activity. Researchers comparing these materials to Roman hydraulic mortars discovered similarities in lime composition and aggregate density. Some plaster samples contain microscopic volcanic particles and crushed ceramics that may have improved durability through pozzolanic reactions. Chemical processes also found in Roman marine concrete. When lime reacts with volcanic minerals and water, it can create crystalline structures resistant to cracking and moisture penetration. If confirmed, this would mean medieval builders in Qadisha possessed practical knowledge of advanced mortar chemistry long after the fall of Rome. Even more puzzling is the way certain frescoes survive inside partially ventilated caves where condensation should have destroyed organic pigments centuries ago. Some historians suspect natural mineral salts inside the limestone may have unintentionally stabilized pigment layers, while others argue the builders deliberately selected microclimates with controlled humidity. The effect is haunting. In some chapels, faces painted centuries ago still emerge faintly from the darkness as if preserved outside normal time. Many structures in Qadisha were designed not to be seen. Several hermit caves are almost invisible from the valley floor because they were built behind natural shadows, vegetation, or rock folds. Some entrances can only be approached from narrow ledges hidden along the cliff face. This has led historians to believe the valley functioned as a refuge during periods of persecution under Mamluk and Ottoman rule. Entire communities may have survived here undetected for decades, but the logistics remain difficult to explain. Supplying isolated cliff chambers with food, oil, parchment, timber, and drinking water across generations would have required highly organized transport routes. Yet very little evidence of large-scale lifting systems survives. In some places, archaeologists found beam holes cut into cliff faces, suggesting suspended wooden walkways once connected hidden sections of the valley. Most have long since collapsed into the gorge below. Another unexplained feature involves sound. Several small chapels produce unusually strong echoes despite their tiny size. A whisper near certain walls can resonate throughout the chamber for several seconds. Acoustic researchers studying stone religious architecture note that curved ceilings and irregular limestone surfaces can amplify specific vocal frequencies. The phenomenon resembles acoustic effects documented at Maya temples like Chichen Itza and underground ritual chambers in Cappadocia. Whether intentional or accidental, the result would have transformed religious chants into deep resonating sounds echoing through darkness and candle smoke. For isolated monks, these spaces may have felt less like buildings and more like living interiors of the mountain itself. Do you think Qadisha Valley was simply a hidden religious sanctuary, or the remains of an ancient survival system far more advanced than historians realize? Share your thoughts in the comments below. Mountains of western Syria hide one of the most terrifying engineering mysteries of the medieval world. Crac des Chevaliers rises above the surrounding valleys like a stone machine built to survive forever. For more than 800 years, earthquakes destroyed nearby cities, empires vanished, and armies repeatedly attacked its walls. Yet the fortress endured, not simply because it was massive, but because many of its engineering principles appear strangely advanced even by modern standards. Although local populations had known the fortress for centuries, Crac des Chevaliers entered major archaeological and military studies during the 19th century, when European explorers began documenting its scale and preservation. What researchers discovered shocked historians. This was not merely a medieval castle. It was one of the most sophisticated military structures ever constructed before the industrial era. Expanded primarily by the Knights Hospitaller during the 12th and 13th centuries, the fortress covers nearly 3 hectares and stands more than 650 meters above sea level. Historical estimates suggest thousands of masons, engineers, laborers, and soldiers contributed to its construction across generations. But the deeper archaeologists examined the fortress, the stranger its engineering became. Most medieval fortifications relied on static defensive principles. Crac des Chevaliers appears to have operated differently. Its walls behaved less like rigid barriers and more like an adaptive structural system. The outer defensive walls reach nearly 3 meters in thickness, while inner sections become even heavier. Some towers exceed 9 meters thick at their bases. Yet despite their enormous mass, many surviving sections do not behave like completely rigid stone structures. Modern engineers studying the fortress observed several anomalies. Certain layers of stone appear to contain slight flexibility. Mortar composition changes between structural zones, and impact fractures often stop spreading before catastrophic collapse occurs. This is highly unusual for a 12th century fortress. In modern earthquake engineering, rigid buildings often fail because shockwaves transfer directly through continuous stone or concrete. Crack appears designed to interrupt or disperse those forces. Researchers have compared this effect to primitive seismic damping systems. The fortress also relies heavily on curved and angled surfaces instead of simple vertical walls. During medieval sieges, trebuchet projectiles weighing more than 100 kilograms could strike walls at speeds estimated between 100 and 160 kilometers per hour. Under repeated bombardment, ordinary medieval masonry should have shattered, yet crack survived centuries of attacks with surprisingly limited structural failure. The angled geometry may have redirected impact energy rather than absorbing it directly, a principle similar to modern blast-resistant military engineering. The disturbing question is not whether the fortress was strong. The real mystery is how medieval builders understood force distribution so effectively without modern mathematics, computer simulation, or material science. This is where Crac des Chevaliers becomes truly difficult to explain. Syria lies near several active tectonic fault systems connected to the Dead Sea Transform Fault Zone, one of the most seismically dangerous regions in the eastern Mediterranean. Throughout history, devastating earthquakes repeatedly struck the area. The earthquake of 1170 severely damaged cities across Syria, while the massive earthquake of 1202 may have killed more than 1 million people across the eastern Mediterranean, according to some historical estimates. Later, earthquakes continued affecting the region for centuries, and yet Crac survived. Not perfectly intact, but remarkably functional compared to surrounding settlements. Modern structural analysis revealed several engineering characteristics that may explain why. The fortress walls are not completely uniform. Instead of behaving as one continuous rigid mass, many sections appear compartmentalized. Internal chambers, layered stone arrangements, hidden cavities, and separated support zones may have helped disperse seismic energy before it could destroy entire structures. Some interior corridors are strangely narrow, asymmetrical, and irregular. Originally believed to be simple military passageways, newer theories suggest these spaces may have unintentionally functioned as pressure relief zones during earthquakes. Even more mysterious is the fortress mortar itself. Chemical studies of surviving materials revealed lime mixtures containing volcanic or silicate-rich compounds. In some areas, the mortar hardened similarly to hydraulic compounds used in later engineering traditions. This matters because flexibility is critical during earthquakes. If mortar becomes too brittle, stone walls crack immediately under vibration. But if mortar retains slight elasticity, structures can absorb and distribute seismic stress more effectively. Roman engineers achieved similar effects centuries earlier using pozzolana volcanic concrete in structures like the Pantheon. However, Crac's builders operated in an entirely different military environment centuries later. This raises an uncomfortable possibility. Did medieval engineers independently rediscover lost seismic construction principles? Or had fragments of Roman and Byzantine engineering knowledge survived far longer than historians believed? Some scholars argue that Crac evolved through generations of practical experimentation. Every siege and every earthquake may have taught builders how to reinforce weaknesses. Over centuries, the fortress slowly transformed into something resembling a giant engineered survival system rather than a simple castle. Modern finite element simulations conducted on certain surviving sections suggest some curved areas distribute stress more efficiently than later medieval fortifications built hundreds of years afterward. Perhaps the strangest detail of all is how certain damaged sections collapsed outward rather than inward. In most fortress failures, collapsing towers crush internal support systems and destroy core defensive areas. At Crac, some wall geometries appear to redirect structural failure away from critical zones. That implies an understanding of controlled structural sacrifice, a principle central to modern military and earthquake-resistant engineering. Western Syria experiences intense summer heat, yet many interior chambers and side crack remain surprisingly cool even today. This effect was not accidental. The fortress incorporates vaulted ceilings, elevated ventilation shafts, narrow thermal corridors, and carefully positioned airflow channels that naturally regulate temperature. Hot air rises through upper openings, while denser cool air moves through lower passageways, creating passive circulation without mechanical assistance. Modern architects describe this as passive thermal regulation, yet Crack implemented the concept centuries before industrial ventilation systems existed. Some underground chambers maintain relatively stable temperatures because of the enormous thermal mass of limestone walls. In several storage areas, temperature fluctuations remain dramatically lower than external conditions, even after centuries of exposure. This may explain how the fortress stored food supplies during prolonged sieges. Historical accounts suggest Crack could support thousands of defenders for extended periods. That required more than military strength. It required environmental control, water management, food preservation, and thermal stability. In many ways, the fortress functioned like a giant stone refrigeration system powered entirely by physics. Viewed from above, Crac des Chevaliers reveals astonishing geometric precision. Defensive sightlines overlap with minimal blind spots, arrow slits align across multiple elevations, and curved towers maximize visibility while reducing exposed attack angles. This level of military geometry becomes even more remarkable considering the terrain itself. The fortress was constructed atop an uneven mountain ridge rather than a flat-engineered platform. Yet, despite the difficult landscape, its defensive symmetry remains highly organized. Some historians compare its strategic planning to Renaissance fortifications developed centuries later after gunpowder artillery transformed military architecture. But Crack predates many of those engineering concepts entirely. The fortress appears to anticipate future defensive principles long before the technologies that supposedly inspired them even existed. Beneath Crac des Chevaliers lies a network of tunnels, storage chambers, water systems, and hidden passageways that remains only partially explored. Many areas are still too dangerous to excavate because of collapse risks. What makes the underground system strange is that some chambers have no obvious military purpose. They're too narrow for troop movement and too isolated for ordinary storage. Some researchers believe these spaces helped regulate temperature and airflow, while others suggest they functioned as emergency survival zones during long sieges. Even today, much of the underground network beneath the fortress remains unmapped. Do you think the builders of Crac des Chevaliers truly understood advanced engineering centuries ahead of their time? Or was this fortress the result of generations of trial and error? Share your thoughts in the comments below. Hidden deep within the dense tropical forests of northern Colombia lies Ciudad Perdida, often called the Lost City. Perched high in the rugged mountains of the Sierra Nevada de Santa Marta, this ancient settlement predates many of the most famous cities of the Americas. Archaeologists believe it was founded around the 8th or 9th century by the Tairona civilization, a sophisticated society that flourished in the region long before the arrival of Europeans. Remarkably, Ciudad Perdida may have been established nearly 6 centuries before the construction of Machu Picchu, yet despite its age and isolation, it reveals an extraordinary level of architectural planning and engineering skill. Even today, surrounded by thick jungle and connected to the outside world only by a long trek through mountainous terrain, the city continues to raise profound questions about the technological capabilities of the people who built it. The settlement is not a single structure but an entire urban landscape carved into steep mountainsides. More than 200 circular and oval terraces were carefully constructed by cutting into the slopes and reinforcing the edges with precisely arranged stone retaining walls. These terraces once supported houses, ceremonial buildings, and communal spaces, forming a multi-level city that cascaded down the mountain like a gigantic staircase. Thousands of stone steps connect the terraces, weaving through the jungle and climbing the rugged terrain in carefully designed pathways. What makes this achievement extraordinary is the environment itself. The Sierra Nevada region experiences heavy tropical rainfall throughout much of the year, and steep slopes combined with saturated soil would normally lead to frequent landslides and erosion. Yet Ciudad Perdida has remained structurally stable for more than 1,000 years. Archaeological studies reveal that the builders engineered an advanced system of drainage channels beneath the terraces, allowing rainwater to flow safely downhill without undermining the foundations. Layers of stone, gravel, and compacted soil function almost like a natural filtration system, dispersing water pressure and preventing destructive runoff. Such hydraulic planning suggests that the Tairona possessed an advanced understanding of environmental engineering, even though they left behind no written technical records explaining how this knowledge was developed. One of the most striking features of Ciudad Perdida is the monumental staircase that leads up to the city itself. Visitors must climb more than 1,200 ancient stone steps to reach the upper terraces. These steps follow the natural curves of the mountain and appear remarkably consistent in height and spacing, allowing travelers to ascend steep terrain with surprising ease. Constructing such a pathway would have required enormous labor, organization, and coordination. The builders would have needed to transport countless stones through dense jungle and up steep slopes without the aid of wheeled vehicles or large draft animals. How the Tairona managed this logistical challenge remains uncertain. Some researchers believe large work crews may have moved the stones using wooden rollers, ropes, and human strength, but no clear evidence of these methods has been preserved. The mystery of transporting and positioning massive building materials in such an inaccessible landscape continues to puzzle archaeologists. Perhaps the most intriguing aspect of the lost city, however, lies in the remarkable stonework that holds the entire settlement together. The terraces and retaining walls are built from carefully shaped stones that fit together with surprising precision. Although the masonry is not identical to the polygonal stone techniques seen in the Inca world, many of the stones at Ciudad Perdida align so closely that gaps between them are minimal, creating walls that remain stable despite centuries of heavy rainfall, shifting soil, and encroaching vegetation. The precision of this construction becomes even more impressive when considering the technological limitations of the era. The Tairona did not possess advanced metal tools like hardened steel chisels, and yet they were able to cut, shape, and position large stones with a degree of control that suggests sophisticated craftsmanship. Some archaeologists propose that the builders used hammerstones combined with abrasive sand and water to gradually grind the rock into shape, but this theory still leaves many questions unanswered. The surfaces of certain stones appear unusually smooth, while others show subtle curvature that allows them to lock into place with neighbouring blocks. This indicates that the builders were not simply stacking rough rocks, but carefully selecting and modifying each piece so that it would fit within a stable structural system. Even today, modern engineers studying the terraces have noted that the stonework distributes weight and pressure in a way that helps prevent collapse on steep slopes. Achieving such structural reliability without modern surveying equipment or precise measuring tools suggests a deep empirical knowledge of stone behaviour and structural balance. Beyond the terraces themselves, the city reveals a complex urban design that hints at a thriving population and a highly organised society. Archaeologists believe that thousands of people once lived here, occupying homes built atop the stone platforms while gathering in open plazas for trade, ceremonies, and social life. The layout of the city appears to follow a carefully planned pattern, with clusters of terraces connected by pathways that guide movement throughout the settlement. Certain areas seem to have been reserved for ceremonial purposes, while others served as residential districts. The arrangement of these spaces implies a social structure in which architecture played a role in shaping communal interactions and religious practices. Yet despite decades of archaeological research, many aspects of the city's organisation remain unclear. The dense jungle that now surrounds the ruins may conceal additional structures still waiting to be discovered, suggesting that Ciudad Perdida could represent only a portion of a much larger network of settlements connected across the mountains. Another enduring mystery concerns the disappearance of the city itself. By the 16th century, during the early period of Spanish exploration in northern South America, the settlement appears to have been abandoned. Historians believe that diseases introduced by Europeans, combined with a disruption of indigenous societies during colonization, may have caused the inhabitants to leave the city and disperse into surrounding regions. However, historical records from Spanish explorers make almost no direct mention of such a large mountain settlement, raising the possibility that the city had already faded from memory by the time Europeans arrived. Over the following centuries, the jungle slowly reclaimed the terraces and stairways, hiding the ruins beneath thick vegetation. It was not until the early 1970s that treasure hunters searching for ancient artifacts stumbled upon the site, bringing the lost city back into the awareness of the modern world. Today, Ciudad Perdida remains one of the most fascinating archaeological sites in the Americas. Its terraces, stairways, and precisely built stone walls demonstrate the remarkable ingenuity of the Tairona civilization, a culture capable of transforming a steep tropical mountainside into a complex urban centre. Yet the more researchers study the ruins, the more questions arise. How were such refined stone-cutting techniques achieved without advanced metal tools? How were heavy building materials transported through rugged jungle terrain and assembled with such stability? And how could a city of this scale remain hidden beneath dense forest for centuries? The lost city continues to challenge modern assumptions about ancient technological capabilities, suggesting that the people who built it possessed engineering knowledge far more advanced than we once believed. In your opinion, how are the ancient Tairona people able to cut and fit stones with such remarkable precision without advanced metal tools? What technique do you think they might have used? Share your thoughts in the comments below. Central Italy, about 16 kilometers north of Rome, hides the ruins of Veii beneath forests and volcanic stone. But under the silent ground lies one of the most disturbing engineering mysteries of the ancient world. A city that may have mastered underground hydraulics centuries before Rome itself understood how to control water on an industrial scale. Veii was once the richest Etruscan city in the region, rivaling early Rome in both military power and technology. Ancient Roman historians like Livy described it as a city so fortified and advanced that Rome needed nearly 10 years to conquer it, finally capturing it around 396 BCE under the general Marcus Furius Camillus. Yet what archaeologists later uncovered beneath Veii raised a more unsettling question. How did a civilization more than 2,400 years ago create underground systems so precise that some still function today? The rediscovery of Veii began seriously in the 19th century, but the real shock came during modern excavations in the 20th century, when archaeologists mapped massive subterranean hydraulic tunnels known as cuniculi. At first, researchers believed they were simple drainage channels, They were wrong. The deeper they explored, the stranger the system became. These cuniculi form a vast underground network carved directly into volcanic tufa bedrock. Some tunnels stretch for kilometers beneath the ancient plateau, intersecting with wells, reservoirs, hidden shafts, and agricultural drainage systems. What makes them extraordinary is not just their scale, but their precision. Many passages maintain an almost perfectly controlled gradient over long distances. Modern surveys found that several tunnels deviate by only a few centimeters over hundreds of meters, a level of accuracy difficult to achieve even with later medieval technology. The mystery becomes even more difficult to explain when considering the working conditions. Many cuniculi are extremely narrow, forcing workers to crawl through darkness while cutting through hard volcanic stone. There was no modern lighting, no laser leveling equipment, and no advanced surveying instruments. Yet the tunnels rarely flood catastrophically and maintain stable water flow even after more than 2 millennia. Engineers studying the system have compared parts of it to early Roman aqueduct logic, except Veille's tunnels predate many major Roman hydraulic achievements by centuries. Some archaeologists believe the cuniculi were designed not only for drainage, but also for controlling underground water pressure beneath the city. This theory emerged after researchers noticed that certain tunnels appear strategically positioned to reduce hydrostatic stress inside the plateau itself. In other words, the Etruscans may have understood that trapped groundwater could destabilize foundations long before formal geological engineering existed. Similar concepts would not become common in Europe again until far later. The volcanic tufa surrounding Veii added another layer of complexity. Tufa is easier to carve than granite, but it is unstable when saturated with water. If drainage is poorly managed, sections can collapse. Yet many tunnels at Veii survived earthquakes, floods, and erosion for over 2,000 years. Some are still operational during seasonal rains. This durability has led some modern engineers to argue that the Etruscans possessed a far deeper understanding of local geology than previously assumed. Even more mysterious is how the tunnels were planned. Certain cuniculi intersect at surprisingly accurate angles, despite being excavated underground from multiple directions. In some sections, the ceilings curve smoothly in ways that distribute pressure naturally, similar to techniques seen later in Roman vaulted construction. Tool marks inside several tunnels suggest organized excavation methods rather than random digging, but no surviving Etruscan texts fully explain the techniques used. The hydraulic sophistication of Veii becomes even clearer when compared with neighboring civilizations of the same period. Around the 5th century BCE, many European settlements still relied on open drainage ditches vulnerable to contamination and collapse. Veii, meanwhile, operated hidden subterranean systems capable of redirecting water across difficult terrain while protecting urban structures above. Some researchers argue that Rome's later mastery of aqueducts and sewer engineering may have originated directly from Etruscan knowledge absorbed after Veill's conquest. One of the strongest pieces of evidence supporting this theory is the Roman sewer known as the Cloaca Maxima. Traditionally celebrated as a Roman engineering triumph, parts of its design resemble Etruscan underground water systems discovered at Veii and other Etruscan cities. Ancient writers themselves admitted that early Roman kings were heavily influenced by Etruscan builders. In many ways, Veii may represent the missing technological bridge between primitive Iron Age settlements and the monumental infrastructure of the Roman Empire. But Veill's mysteries do not end underground. Above the tunnels stood massive temples, workshops, defensive walls, and elite residences built with techniques still debated today. The famous Portonaccio Temple once displayed enormous terracotta statues, including the celebrated Apollo of Ver from the late 6th century BCE. These sculptures reveal firing technology far beyond what many historians expected from the era. Large terracotta objects normally crack under uneven heating, especially when exposed to rapid cooling. Yet the Apollo survived in remarkable condition despite centuries underground. Researchers studying Etruscan kilns discovered evidence of sophisticated airflow control systems capable of distributing heat more evenly across large chambers. Some firing temperatures may have exceeded 900 degrees Celsius. That level of thermal control required careful oxygen management and highly organized fuel distribution. Similar large-scale ceramic firing techniques would later become central to Roman industrial production. Veii also demonstrates strange architectural resilience. Several surviving foundations show unusually stable block placement, using tightly fitted volcanic stone with minimal mortar. In some locations, the arrangement appears designed to absorb small ground movements instead of resisting them rigidly. Modern earthquake-resistant structures often use comparable principles by allowing controlled movement during seismic stress. Whether the Etruscans intentionally understood this effect remains unknown, but the survival of certain structures through centuries of regional seismic activity is difficult to ignore. Another unresolved mystery involves the rumored military tunnels connected to Veii's final siege. According to Roman accounts, soldiers under Camillus secretly dug through underground passages to enter the city during the final assault. Historians long considered the story partly legendary. However, later excavations confirm that Veii truly possessed an enormous network of subterranean routes beneath its sacred and defensive zones. Some archaeologists now believe the Roman story may have been based on real engineering operations. Modern ground-penetrating radar surveys continue to detect buried anomalies beneath unexplored sections of Veii. Several possible underground chambers remain inaccessible. Some may be collapsed hydraulic structures, others could be ritual spaces, storage systems, or additional tunnel complexes still hidden beneath volcanic soil. Even today, large portions of the city remain unexcavated. Do you think the Romans truly invented their greatest engineering technologies? Or did they inherit secrets from forgotten civilizations like Veii? Share your thoughts in the comments below. Amethyst stood along the southern coast of Cyprus overlooking the Mediterranean Sea. Archaeologists began systematic excavations there in the late 19th century after French expeditions uncovered massive limestone blocks, underground chambers, and inscriptions linked to one of the island's oldest kingdoms. Later excavations revealed an enormous acropolis, harbour installations, ritual caves, water systems, temples dedicated to Aphrodite, and one of the strangest stone artifacts ever discovered in the Eastern Mediterranean, a gigantic monolithic limestone vase weighing more than 14 tons. Each excavation season exposed something new. Early digs uncovered Phoenician inscriptions and defensive walls. Mid-20th century excavations revealed hidden cisterns and tunnel systems beneath the city. More recent marine archaeology projects identified submerged harbour structures and erosion-resistant foundations beneath the shoreline. But the deeper researchers dug into Amethyst, the more the site stopped looking like a simple Iron Age city and started resembling an advanced engineering experiment far ahead of its time. The most famous object from Amethyst is the colossal stone vase carved from a single limestone block near the summit of the Acropolis. The structure stands roughly 1.85 meters high, with walls thick enough to survive more than 2 millennia of earthquakes, humidity, and coastal erosion. The mystery is not simply its size. It is how ancient workers transported it uphill. The Acropolis rises approximately 90 meters above sea level, and the slopes surrounding it are steep and uneven. Modern engineering estimates suggest that dragging a 14-ton object up such terrain using primitive rope systems would require enormous manpower. lubrication techniques, wooden rollers, or advanced pulley systems. Yet no definitive evidence of those transport mechanisms has ever been found at Amathus. Researchers often compare the problem to the unfinished megaliths at Yangshan Quarry or the stone transport mysteries of Baalbek. However, unlike Baalbek, Amathus belonged to a smaller island kingdom with far fewer available labour resources. The vase itself raises even more questions. Its internal curvature is unusually symmetrical. Tool marks suggest controlled carving techniques rather than rough extraction. Some microscopic surface analyses indicate repeated abrasion using harder mineral compounds, possibly quartz-rich sand mixed with water. Experimental archaeologists attempting to recreate similar surfaces using Bronze Age tools found the process dramatically slower than expected. Several sections of the stone show evidence of smoothing so consistent that some researchers compare it to rotary abrasion methods used centuries later in advanced Hellenistic workshops. No one fully understands how Iron Age craftsmen on Cyprus achieved this precision. Beneath Amathus lies one of the least understood hydraulic systems in the ancient Mediterranean. Hidden below the city are underground tunnels, deep cisterns, narrow channels carved directly into bedrock, and carefully sloped water conduits designed to collect, transport, and preserve water through Cyprus's long dry seasons. This system is one of the greatest unsolved engineering mysteries at the site. Cyprus receives relatively low annual rainfall compared to regions like mainland Greece. Long drought periods would have threatened any coastal settlement. Yet Amathus survived for centuries in a semi-arid environment while maintaining a large urban population. Archaeologists discovered that many channels inside the underground system were cut with extremely small gradients, sometimes only a few centimeters of drop over long distances. Even today, modern gravity-fed water systems rely on similar principles. What shocked researchers was the accuracy. Several conduits maintain slope deviations small enough to keep water flowing steadily without excessive turbulence or sediment buildup. If the angle became too steep, erosion would damage the channels. Too shallow, and water stagnation would occur. Somehow, the builders achieved a balance remarkably similar to later Roman aqueduct engineering. This has led some historians to question whether the hydraulic knowledge at Amathus developed independently, or whether ancient Mediterranean civilizations exchanged engineering concepts far earlier than previously believed. The tunnels themselves deepen the mystery. Some extend through solid limestone with surprisingly smooth walls and consistent widths. In several locations, archaeologists found ventilation shafts that may have regulated temperature and humidity inside the underground reservoirs. Thermal measurements taken in modern surveys show certain underground chambers remain significantly cooler than surface temperatures, even during intense summer heat. This suggests the system may have functioned not only as water storage, but also as a primitive climate stabilization network. Researchers often compare these features to Persian Qanat systems and underground cooling structures found in ancient Iranian desert cities. But Amathus predates many of the best-known examples. The waterproofing methods are equally puzzling. Fragments of coating material recovered from cistern walls contain lime-based compounds mixed with volcanic or marine-derived particles. Laboratory studies suggest these mixtures reduced water penetration and improved durability. Some samples show chemical behavior surprisingly similar to early hydraulic cement. This is extraordinary because advanced waterproof mortar technologies are usually associated with Roman concrete centuries later. Another unresolved question involves maintenance access. Certain tunnels are too narrow for large-scale cleaning operations, yet sediment accumulation appears lower than expected. Some researchers suspect the builders intentionally engineered water flow speeds to minimize deposits naturally, a sophisticated hydraulic concept difficult to prove but hard to ignore. Even more mysterious are reports of blocked tunnel branches leading deeper beneath the Acropolis. ground-penetrating radar surveys detected anomalies suggesting additional buried chambers or collapsed passageways still hidden underground. Some archaeologists believe parts of the hydraulic network remain undiscovered because centuries of earthquakes buried major entrances beneath debris. If true, the known system may represent only a fraction of the original infrastructure. The harbour of Amathus presents another engineering anomaly. The southern coast of Cyprus experiences strong wave energy, salt corrosion, and seasonal storm activity. Ancient ports in such environments were usually destroyed, buried by sediment, or heavily eroded over time. Yet parts of Amathus' harbour foundations survived for more than 2,000 years. Marine archaeologists identified massive limestone blocks arranged in ways that appear designed to dissipate wave force rather than simply resist it. Some structures angle slightly against incoming currents, reducing direct impact pressure. Modern coastal engineers noticed similarities between these layouts and later Roman breakwater concepts. The harbour orientation may also have exploited natural coastal hydrodynamics. Sediment studies suggest water circulation near the harbour reduced long-term silt accumulation, allowing ships to continue operating without constant dredging. This level of environmental adaptation is difficult to explain for a relatively small Iron Age kingdom. Some submerged sections also show unusually tight stone fitting with minimal gaps. This reduced water intrusion and structural weakening caused by repeated wave compression. Comparable techniques appear in parts of Alexandria and ancient Phoenician ports, but Amathus remains one of the least studied examples. Excavations on the Acropolis show that several structures at Amathus were built in alignment with the sun during seasonal transitions. Some researchers also believe the temple complex may have been connected to the appearance cycles of Venus, the celestial body associated with Aphrodite. If true, this suggests the people of Amathus observed the sky over many generations. Experts have also noted that the precision of these alignments is similar to astronomical ritual sites in Egypt and the Levant. What makes Amathus unique is that these alignments were integrated into a functioning coastal city, combining astronomy, religion, navigation, and ancient engineering. Do you think the lost underground sections of Amida still hide technologies or structures we haven't discovered yet? Share your thoughts in the comments below. At the mouth of the River Tyne in northern Britain, where freezing North Sea winds collide with endless rain and salt-filled air, the ruins of Arbaea Roman forts still stand after nearly 1,800 years. Built at the outer edge of the Roman Empire, Arbaea was not supposed to survive this long. Yet beneath its collapsed walls lies evidence of engineering methods so advanced that some archaeologists believe the Romans understood climate control, material chemistry, and military logistics at a level centuries ahead of their time. The fort was first identified during excavations in the late 19th century after Roman inscriptions, foundations, and military structures began emerging beneath the modern town of South Shields. Archaeologists soon realized Arbaea was not an ordinary frontier fort. It functioned as one of the most important supply bases supporting Hadrian's Wall, feeding and equipping thousands of Roman soldiers stationed across northern Britain. But the deeper researchers dug, the stranger the site became. Unlike many Roman forts designed mainly for defense, Arbaea appears to have been engineered around logistics efficiency. The location itself was strategic. Positioned directly beside the River Tyne, cargo ships from across the empire could unload grain, oil, wine, and military supplies almost directly into the fort. Excavations revealed enormous granaries capable of storing vast quantities of food. Yet these warehouses contained one of the site's first major mysteries. The granary floors were raised above the ground on rows of carefully spaced stone pillars, creating an empty air chamber underneath. At first glance, the design seems simple, but in northern Britain's climate, this may have been the difference between survival and disaster. South Shields receives heavy rainfall throughout the year, with humidity levels frequently above 80%. In such conditions, stored grain can rot rapidly through mold growth and moisture absorption. Modern agricultural storage facilities use ventilation systems and elevated flooring for exactly this reason. Yet the Romans were implementing similar principles nearly 2,000 years earlier. Experimental archaeology studies comparing reconstructed Roman granaries with ordinary storage buildings have shown significantly lower moisture accumulation inside elevated Roman designs. The airflow beneath the floor reduced condensation and stabilized temperatures. Some researchers believe Arbea's engineers may have unintentionally created one of the earliest passive climate control systems in Europe. Others argue it was no accident at all. The Roman military depended on predictable food preservation. A single failed grain supply during winter could destroy entire frontier garrisons. But perhaps the greatest mystery surrounding Arbea is not its storage system. It is the material holding the fort together. Most ancient structures exposed to the North Sea climate deteriorate rapidly. Salt carried by sea winds penetrates stone and mortar, causing repeated cycles of expansion and cracking. Modern concrete structures near coastlines often require major repairs within decades because chloride ions from salt water corrode internal materials and weaken the structure from within. Yet parts of Arbea's foundations have remained remarkably stable after almost 18 centuries of freezing temperatures, rain, and marine exposure. Archaeologists studying surviving mortar samples discovered unusual mineral compositions compared with standard Roman concrete found in southern Europe. Traditional Roman concrete, especially around the Mediterranean, often relied on volcanic ash known as pozzolana. When mixed with lime and seawater, pozzolanic concrete produced exceptionally durable chemical reactions. Some Roman harbour structures in Italy have survived for over 2,000 years because of this material. Northern Britain, however, lack the volcanic ash resources available near Rome. Arbea's builders appear to have adapted. Analysis of mortar fragments suggests they may have altered lime mixtures using locally available sand, crushed ceramics, and mineral-rich aggregates capable of resisting moisture penetration. Some microscopic studies even indicate the presence of crystalline formations inside cracks, suggesting the mortar may have partially self-sealed over time when exposed to water. This phenomenon has drawn comparisons to modern self-healing concrete technologies currently being developed by material scientists. In modern experiments, specialized minerals or bacteria are added to concrete, so cracks automatically fill when exposed to moisture. Arbea's mortar obviously was not engineered using modern chemistry, yet the similarities are difficult to ignore. Researchers still debate whether the Romans intentionally designed the mixture for northern marine conditions or whether the effect emerged accidentally through centuries of mineral interaction. The mystery deepens when Arbea is compared with other Roman frontier forts in Britain. Many nearby structures suffered far worse deterioration despite being younger or less exposed. Arbea's unusual resilience suggests its engineers understood something highly specific about local environmental stress. The question is, how? Another strange detail discovered at the fort involves the soldiers themselves. Inscriptions found at the site reference Tigris boatmen and archers from Mesopotamia, modern-day Iraq and Syria. These men originated from some of the hottest regions of the Roman Empire, yet they were stationed in one of its coldest and wettest frontiers. This has led historians to reconsider how knowledge travelled through the empire. Roman military units did not simply transport weapons. They carried engineering techniques, architectural ideas, and environmental knowledge from distant regions. Some researchers suspect Eastern engineers may have contributed specialized construction methods adapted from water management systems used in Syria and Mesopotamia. Techniques originally developed for preserving water in deserts may have been reimagined at Arbea for resisting cold moisture instead. The fort also contains evidence of advanced heating systems. Excavations uncovered remains of hypercourse technology beneath certain buildings, particularly command areas and officers' quarters. The hypercourse worked by circulating hot air beneath raised floors and inside wall channels. Essentially, it functioned as an ancient central heating system. What makes this remarkable is the location. Arbea sat at the edge of the Roman world, thousands of kilometers from Rome itself. Maintaining hypercourse systems required fuel, engineering expertise, and constant maintenance. Wood consumption alone would have been enormous. Some estimates suggest Roman bathhouses and heated complexes consumed several tons of wood annually. The existence of such systems at a remote frontier fort implies Arbea was far more strategically important than historians once believed. The scale of imported goods found at the site supports this idea. Archaeologists uncovered pottery from North Africa, olive oil containers from Spain, glassware from continental Europe, and luxury goods transported across thousands of kilometers. This reveals the astonishing efficiency of Roman logistics. Without engines, railways, or modern ports, the empire maintained a supply network stretching from the Mediterranean to the freezing edge of Britain. To modern researchers, this may be Arbea's greatest mystery of all. The Roman Empire controlled nearly 5 million square kilometers at its height. Coordinating supplies across such distances should have been nearly impossible with ancient technology. Yet forts like Arbea remained operational for centuries. Grain arrived before winter, building materials reached remote coasts, specialized troops from Syria served beside soldiers from Gaul and Germany. Somehow, the system worked. What do you think made Arbea's engineering survive nearly 1,800 years against the brutal North Sea climate? Was it lost Roman technology, advanced material science far ahead of its time, or something historians still haven't fully discovered? Let us know your thoughts in the comments below. County Sligo in Western Ireland hides Carrakiel megalithic cemetery across the Brickleave Mountains, like a forgotten machine made of stone. Built more than 5,000 years ago, the site contains passage tombs older than the pyramids of Giza. Yet what terrifies archaeologists is not its age, but the possibility that Neolithic builders understood engineering, structural balance, astronomy, and landscape geometry at a level that should not have existed in prehistoric Europe. Although local people had known about the cairns for centuries, the first major archaeological surveys only began in the early 1900s, when researchers uncovered dozens of hidden passage tombs spread across the mountain ridges. Excavations revealed cremated human remains, polished stones, bone fragments, and carefully constructed chambers sealed for thousands of years beneath enormous masses of limestone. Archaeologists expected primitive burial structures, but what they found instead looked disturbingly advanced for a civilization that supposedly lacked complex engineering knowledge. One of the greatest mysteries surrounding Carrakiel is its location. The cemetery was constructed between roughly 3,400 and 3000 BCE on steep limestone mountains, more than 300 meters above sea level. Even today, transporting building materials across the region is difficult because of exposed rock surfaces, unstable slopes, sudden weather changes, and narrow mountain routes. Yet, Neolithic builders somehow transported and positioned stones weighing several tons without metal tools, wheeled vehicles, cranes, or known draft animals. Archaeologists estimate that some cairns contain thousands of tons of limestone, and experimental archaeology projects suggest moving a single 2-ton slab uphill using rope and log systems could require more than 150 people working in precise coordination. The mystery becomes even deeper when researchers examine the chambers themselves. Several internal stones were fitted together, with surprising precision to reduce stress concentration and distribute weight more evenly, a principle comparable to later megalithic engineering seen at Newgrange and even the stonework of Sacsayhuaman in Peru. The question remains controversial among researchers. How could societies with supposedly primitive technology organize massive labor forces, transport enormous stones through dangerous terrain, and engineer stable chambers capable of surviving for more than 5 millennia? Some archaeologists believe the builders possessed advanced practical knowledge of load balancing, friction reduction, seasonal ground conditions, and coordinated force distribution. It may not have been theoretical engineering in the modern sense, but rather knowledge refined through generations of observation and experimentation. The most technically disturbing feature at Carrakeel may be its roofing systems. Several passage tombs contain corbelled roofs, where layers of stone gradually overlap inward until the chamber closes at the top. Although the concept appears simple, structurally it is extremely dangerous because every layer transfers weight downward and inward. A small error in angle or placement can destabilize the entire chamber and eventually force the walls outward until collapse occurs. Yet many of Carrakeel's chambers have survived for more than 5,000 years despite exposure to Atlantic storms, freezing winters, moisture expansion, seismic micro-vibrations, and continuous gravitational stress. Modern engineers studying ancient dry stone architecture note that corbelled chambers rely on extremely delicate compression physics. The inward angle of each slab determines whether forces stabilize naturally or slowly destroy the structure over centuries. What makes Carrakeel extraordinary is that these chambers were built entirely without mortar. The stones simply hold themselves together through pressure and balance alone. Even more mysterious are the so-called roof box openings, found above the entrances of certain passage tombs. These narrow gaps allow sunlight to penetrate deep into the chambers during specific seasonal events, especially around solstices and transitional solar periods. This creates an extraordinary engineering paradox. The builders somehow had to preserve structural integrity, reduce roof pressure, prevent long-term collapse, and maintain a carefully calculated solar opening at the same time. Achieving all of this with Stone Age tools should have been incredibly difficult. Researchers comparing Carrakeel with Newgrange discovered that both sites appear to use controlled light entry systems, but Carrakeel's mountainous location makes the geometry even more complex because the surrounding peaks constantly alter horizon angles and solar trajectories. To align sunlight correctly, the builders may have observed seasonal solar movement for decades or even generations. Some archaeoastronomers believe the chambers were not merely tombs, but astronomical devices designed to track cyclical celestial events. Others argue the roof boxes may have served ritual functions connected to death, rebirth, or ancestor worship. However, the deeper mystery remains structural. Modern reconstructions show that alignment errors of only a few degrees could dramatically increase roof instability over time, yet many chambers remain standing after more than 5,000 years. Compared to numerous Bronze Age structures across Europe that partially collapsed after much shorter periods, Carrakeel's survival suggests its builders understood stone compression mechanics far better than traditionally believed. Several passage tombs at Carrakeel align with the setting sun during the summer solstice. During these brief moments, sunlight travels through narrow stone passages and illuminates the inner chambers. Similar solar alignments appear at sites such as Meeshoa, Stonehenge, and temples in ancient Egypt, but Carrakeel differs in one important way. The cemetery exists within a mountainous horizon system, where surrounding peaks create constantly shifting observation lines that dramatically complicate solar calculations. Researchers using digital horizon modeling discovered that some cairns appear intentionally positioned to interact with specific mountain gaps, where the sun becomes visible during key seasonal periods. This suggests long-term astronomical observation and careful environmental mapping. Some calculations indicate that accurately tracking these solar cycles would require decades of repeated monitoring, implying organized knowledge transferred across multiple generations. For a society without writing, that possibility is remarkable. Another unexplained phenomenon involves sound. Researchers testing the chambers discovered unusual acoustic effects, including low-frequency resonance, amplified echoes, and standing wave vibrations. Inside certain tombs, drum beats and chanting create powerful reverberations that feel disproportionate to the actual chamber size. Similar acoustic anomalies have been documented at ancient sites in Malta and Turkey, including the underground chambers of Hal Saflieni Hypogeum. Some acoustic specialists believe these frequencies can psychologically affect human perception by producing sensations of emotional intensity, disorientation, or altered awareness. Whether these effects were intentional or accidental remains unknown. However, the repeated appearance of resonance-focused spaces across unrelated ancient cultures raises uncomfortable questions about prehistoric architectural knowledge. Did Neolithic builders understand acoustic manipulation through experimentation? Or are modern researchers simply projecting meaning onto structures built for entirely different purposes? No one knows for certain. Carroquel was not designed as a single tomb complex, but as an interconnected ceremonial landscape spread across multiple mountain ridges. From several cairns, observers can see precise sightlines toward valleys, lakes, and distant peaks. Satellite mapping and terrain analysis suggest some tomb placements may have been intentionally positioned to create geometric relationships across the landscape itself. This has led to controversial theories that Carroquel functioned as a seasonal calendar, a ceremonial pilgrimage network, or even a large-scale sacred map connected to celestial observation. Although many of these theories remain speculative, the scale of planning involved is undeniable. The cemetery stretches across several mountain summits over multiple kilometers, requiring coordinated labor, logistical planning, and long-term social stability far beyond what archaeologists once believed possible for Neolithic Europe. One of the greatest tragedies surrounding Carroquel is that early excavations destroyed critical evidence. In the early 1900s, some chambers were opened using blasting techniques. While archaeological recording methods were still primitive by modern standards, as a result, researchers may never fully understand how the tombs were sealed, how their construction evolved, or how their astronomical systems originally worked. Today, technologies like LiDAR, 3D modeling, DNA analysis, and ground-penetrating radar are revealing hidden details beneath untouched cairns. However, many archaeologists believe the most important clues were lost forever during the earliest excavations. Do you think the builders of Carroquel possessed lost engineering knowledge far beyond what history tells us? Or are we still underestimating prehistoric civilizations? Let me know your thoughts in the comments below. In the Judean lowlands of modern-day Israel, beneath dry hills and ruined stone houses, lies Horvat Midras, an ancient settlement hiding one of the most sophisticated underground systems ever carved into rock in the ancient Near East. What archaeologists found beneath the surface was not just a refuge. It was an engineered labyrinth. Narrow tunnels, hidden chambers, ventilation shafts, disguised stone doors, and underground routes aligned with astonishing precision. Even today, researchers still debate how people nearly 2,000 years ago managed to design and excavate such a system without modern surveying tools, artificial lighting, or advanced engineering equipment. Horvat Midras was first surveyed in the late 19th and early 20th centuries, but its true complexity was only understood after extensive archaeological excavations during the 20th century. Located roughly 30 kilometers southwest of Jerusalem, the site appeared at first to be another abandoned settlement from the Roman and Byzantine periods. But beneath collapsed ruins, archaeologists discovered an enormous network of tunnels and hidden chambers cut directly into chalk bedrock. Many passages were so narrow that explorers could only move through them by crawling. Others suddenly opened into storage rooms, cisterns, escape shafts, or hidden halls. The deeper excavations went, the clearer it became that this underground world had been intentionally engineered with remarkable planning and spatial awareness. One of the greatest mysteries surrounding Horvat Midras is the sheer scale of excavation. The underground network extends through hundreds of meters of carved passageways beneath the settlement. The tunnels were cut directly into dense limestone and chalk formations using ancient hand tools. Experimental archaeologists attempting to replicate the excavation process discovered that carving even a single meter into hard stone with Roman-era iron chisels could take dozens of hours. Yet Horvat Midras contains thousands of cubic meters of removed material. That raises a difficult question. How was all of this stone excavated, transported, and hidden without leaving massive spoil piles around the settlement? The engineering challenge becomes even more difficult when considering ventilation and lighting. Ancient workers operated underground in total darkness, with oil lamps producing limited oxygen and dangerous smoke buildup. Modern tunnel systems require careful airflow calculations, but Horvat Midras appears to have solved these problems using passive ventilation nearly 2 millennia ago. Most archaeologists associate the underground system with the Bar Kokhba revolt against the Roman Empire between 132 and 135 CE. During this rebellion, Jewish resistance fighters created hidden tunnel systems across Judea to evade Roman forces, but Horvat Midras appears unusually advanced even compared to other Bar Kokhba hideouts. Several tunnels contain choke points forcing intruders to move one at a time. Others split into confusing branches designed like mazes. Certain chambers were positioned to allow defenders to ambush enemies, emerging from tight corridors. Some entrances were hidden beneath movable stone slabs disguised as ordinary flooring. Military historians have compared aspects of the design to modern asymmetric tunnel warfare. Similar concepts appeared centuries later in medieval escape networks, and even 20th century resistance tunnels during wartime conflicts. Yet Horvat Midras predates many of these systems by more than 1,000 years. One of the most technically fascinating features of Horvat Midras is its ventilation system. Archaeologists identified vertical shafts connecting underground chambers to the surface. At first glance, they seemed random, but later mapping revealed something remarkable. Many shafts were positioned on elevated terrain where natural wind pressure differences could improve airflow underground. This resembles principles used in passive ventilation engineering today. Hot air rising through one shaft would help pull cooler air through another opening, maintaining circulation inside enclosed tunnels. Engineers studying ancient airflow systems noted that some underground chambers at Horvat Midras remain surprisingly breathable, even after centuries of collapse and sediment accumulation. Without proper airflow, oil lamps would quickly consume oxygen and produce carbon monoxide buildup. Yet the tunnel network was clearly designed for extended human occupation. This suggests ancient builders possessed highly developed practical knowledge of underground air circulation through empirical observation alone. The Judean lowlands experience long dry seasons with limited rainfall. Despite this, Horvat Midras contained large underground cisterns capable of storing significant quantities of water. The walls of these reservoirs were coated with hydraulic plaster so durable that some sections remain intact after nearly 2,000 years. Laboratory analysis of ancient Roman and Near Eastern waterproof plaster often reveals combinations of lime, volcanic ash, crushed ceramics, and organic additives that trigger complex chemical reactions during curing. Some researchers compare these ancient mixtures to Roman marine concrete, which famously becomes stronger over time through mineral interaction with water. In certain ancient Mediterranean harbours, Roman concrete has survived for over 2,000 years, while many modern coastal concretes deteriorate within decades. Horvat Midras demonstrates a smaller but equally impressive version of this lost material science. Among the most mysterious discoveries were concealed stone entrances leading into underground passages. Some door slabs were carefully shaped to blend seamlessly into surrounding floors or walls. Several still pivot or slide with surprising efficiency despite centuries underground. Archaeologists studying wear patterns found polished contact surfaces likely designed to reduce friction. Achieving this level of mechanical precision with ancient stone working tools would have required careful shaping and repeated adjustment. The concealment itself was highly sophisticated. Roman soldiers unfamiliar with the settlement could easily walk across hidden entrances without noticing them. This transformed the entire village into a concealed defensive structure integrated directly into daily architecture. Near Horvat Midras stands a mysterious pyramid-shaped stone monument built from large stacked stones without mortar. The structure is relatively small compared to Egyptian pyramids, but its purpose remains uncertain. Some archaeologists believe it served as a memorial tomb. Others argue it may have functioned as a landmark, watchtower, or signalling structure. Its placement offers visibility across major movement corridors through the Judean hills. From its elevated position, observers could monitor travelers approaching from considerable distances. The monument's geometry also remains unusual. Several measurements suggest intentional proportional planning rather than random stacking. While no consensus exists regarding astronomical alignment, researchers continue debating whether the structure had symbolic, military, or ritual significance. The most controversial technical mystery at Horvat Midras involves underground navigation and surveying. Many tunnels maintain remarkably stable directional consistency despite being excavated deep underground with no modern instruments. Some passages connect distant chambers while preserving controlled gradients and alignment accuracy over long distances. This creates a major engineering question. How did ancient builders maintain orientation beneath solid rock? Modern tunneling relies on laser systems, compasses, transit instruments, and detailed mapping. Even in early industrial Europe, tunnel projects frequently failed because excavation teams digging from opposite ends missed each other underground. Yet at Horvat Midras, many connecting passages meet with surprisingly small deviations. Researchers believe ancient surveyors may have used surface reference points combined with rope measurements, plumb lines, sound transmission, or primitive geometric triangulation. Some theories suggest builders exploited natural rock fractures as directional guides, but none fully explain the consistency observed throughout the network. The problem becomes even more difficult considering the environmental conditions underground. Workers operated in darkness, confined spaces, dust, smoke, and low oxygen. Small directional errors compounded over dozens of meters should have caused major misalignments. Instead, Horvat Midras demonstrates a level of spatial planning that many historians believe ancient societies are often unfairly denied. Do you think the builders of Horvat Midras possessed engineering knowledge far beyond what historians normally credit ancient civilizations with? Share your thoughts and theories in the comments below. At the border of Oxfordshire and Warwickshire in England stands a prehistoric monument older than many Egyptian pyramids. The rollright stones were built between roughly 3800 BCE and 2500 BCE, yet some researchers believe their positions may encode lunar and solar alignments so precise that they rival later astronomical sites across Europe. The mystery is not the size of the stones. It is the intelligence hidden in where they were placed. Unlike buried ancient cities, rollright was never truly lost. Local legends about living stones survived for centuries before formal excavations began in the 19th and early 20th centuries. Archaeological surveys later revealed that the site was not one monument, but 3 separate structures built across different eras: the King's Men Stone Circle, the Whispering Knight's Chamber Tomb, and the Kingstone Monolith. Radiocarbon dating and soil analysis eventually showed that these monuments may have been constructed hundreds, possibly over 1,000 years apart, yet somehow they still appear connected by unified design. Among all the mysteries surrounding Rollright, the most controversial is the possibility that the builders intentionally transformed the natural horizon into a prehistoric astronomical instrument. The Kingsmen Stone Circle contains around 70 weathered limestone stones, arranged in an almost perfect circle approximately 31 meters in diameter. At first glance, it appears crude compared to Stonehenge. The stones are uneven, relatively small, and lack the engineered symmetry of later megalithic monuments. But modern topographic studies change that perception completely. Researchers discovered that the monument interacts with the surrounding hills and horizon lines in unusual ways. Certain viewing positions align with winter solstice sunrise, summer solstice sunset, major lunar standstill positions, and cyclical moonrise points connected to the 18.6-year lunar cycle. That last detail is where the mystery becomes extreme. Tracking the lunar standstill cycle requires decades of uninterrupted sky observation. Even advanced civilizations struggled with this. The Babylonians mathematically recorded lunar cycles thousands of years later using written astronomy. Yet the builders of Rollright supposedly had no writing system, no metal instruments, and no known mathematical notation. Still, surveys using laser mapping and astronomical reconstruction software suggest that several sight lines around Rollright correspond closely with ancient celestial events. Some alignments deviate by only a few degrees. For comparison, Stonehenge primarily emphasizes solar alignment. Newgrange in Ireland focuses on winter solstice illumination, while Chaco Canyon in North America tracks solar and lunar cycles through horizon markers. Rollright appears to combine both terrain-based astronomy and monument geometry in a simpler but strangely effective way. What makes this even more difficult to explain is the landscape itself. Unlike Stonehenge, which sits on relatively open plains, Rollright is positioned in uneven highland terrain. The hills surrounding the monument naturally frame sections of the sky. Some archaeologists believe the builders intentionally selected this exact location because the horizon already functioned as a giant observational map. In other words, the monument may not have been built merely on the landscape. It may have been built with a landscape. This raises a disturbing possibility. Prehistoric communities in Britain may have possessed long-term observational astronomy, far more advanced than historians previously believed. The stones themselves are not enormous by megalithic standards. Most are made from local oolitic limestone and weigh between several hundred kilograms to multiple tons. The problem is the terrain. Rollright sits on elevated ground with clay-heavy soil that becomes unstable during rain. Experimental archaeology teams attempting to recreate Neolithic transport methods discovered that moving stones uphill across wet clay dramatically increases resistance. Some simulations suggest that even small stones would require dozens of workers, synchronized rope systems, timber rollers or sledges, and carefully prepared pathways. Yet no large-scale quarry roads or construction infrastructure have been found nearby. More mysterious is the stability of the stones after thousands of years. Many stones are not buried deeply, yet remain upright despite frost expansion, soil erosion, seasonal water saturation, strong upland winds, and gradual ground movement. Modern engineers studying the site proposed that the builders may have intentionally positioned stones on naturally compressed subsoil or hidden limestone shelves beneath the surface. That would require an advanced understanding of ground stability without excavation machinery or geological science. At sites like Göbekli Tepe in Turkey and the Karnak alignments in France, researchers also found evidence suggesting prehistoric builders understood terrain mechanics far better than expected. Rollright may belong to the same category of forgotten engineering intelligence. A short distance from the circle stands the Whispering Knights, a collapsed Neolithic chamber tomb dating to roughly 3800 BCE. Its surviving stone chambers create unusual acoustic effects. Several independent sound experiments found that low-frequency tones resonate inside the structure more intensely than expected for such a small space. Whispered voices can also reflect unpredictably between the stones. This phenomenon appears repeatedly in ancient ritual architecture worldwide. The Hypogeum of Malta amplifies frequencies around 110 Hz. Newgrange creates echo effects within its passage. Maya temples at Chichen Itza generate engineered sound reflections, and ancient Greek theatres manipulated acoustic geometry with remarkable precision. At Rollright, the effect is weaker but still measurable. Some researchers suspect prehistoric ceremonies may have intentionally used resonance, chanting, or drumming to alter psychological states. Low-frequency sound can affect human perception, balance, and emotional response. If intentional, this would mean the builders understood practical acoustic behavior thousands of years before formal physics existed. For centuries, local folklore claimed the stones could move at night or possess supernatural energy. Modern science does not support the legends directly, but geological surveys detected subtle magnetic irregularities around portions of the site. Some theories point toward underground water movement, mineral variations in limestone, localized electromagnetic fluctuations, and buried geological fractures. Curiously, many major megalithic monuments are positioned near underground water systems or tectonic boundaries, including Stonehenge, Avebury, Karnak, and Delphi in Greece. Some geophysicists argue that ancient builders may have unknowingly sensed environmental anomalies through sound, vibration, or animal behavior. Others propose something more radical, that certain prehistoric cultures intentionally sought locations with unusual natural energy patterns. No consensus exists. Radiocarbon evidence suggests that the three main structures at Rollright were not built during the same period. The Whispering Knights may date back to around 3800 BCE, the King's Men to roughly 2500 BCE, while the Kingstone likely belongs to another phase entirely. What makes this strange is that generations separated by centuries continued building within the same landscape while preserving consistent alignments and spatial design. Despite having no writing system, maps, or architectural records, some anthropologists believe this knowledge was passed down through rituals, oral traditions, and repeated sky observation over many generations. Polynesian navigators once maintained highly complex celestial navigation systems without writing, but Rollright appears to suggest an even more advanced continuity of astronomical knowledge. After more than 4,000 years, Rollright may still be preserving a form of knowledge that modern archaeology cannot fully explain. Do you think the builders of Rollright preserved astronomical knowledge through oral tradition alone, or could they have possessed a forgotten system of recording information that has never been discovered? Share your thoughts in the comments below. Forests of Brittany, France still hide a 4,500-year-old stone structure standing almost perfectly intact. La Roche-aux-Fées was built with more than 40 massive stones, some weighing over 40 tons, yet no mortar, no metal clamps, and no advanced machinery were ever found here. Even today, archaeologists still cannot fully explain how Neolithic builders assembled a structure this stable with such precision. The monument was first documented in detail during the 18th and 19th centuries as French antiquarians began surveying prehistoric sites across Brittany. Excavations revealed ceramic fragments and human remains dating to roughly 3000–2500 BCE, placing the structure deep within the late Neolithic period. But unlike many collapsed European dolmens, La Roche-aux-Fées remained astonishingly preserved, immediately raising questions about the engineering knowledge of its builders. What makes the site so disturbing is not simply its size. Europe contains many megalithic monuments. The real mystery is the level of structural understanding hidden inside the monument's design. The corridor stretches nearly 20 meters long and is covered by enormous capstones balanced across upright pillars. Modern structural engineers studying the site notice something unusual. The stones are not randomly stacked. Their weight appears deliberately distributed to reduce concentrated stress points. In several areas, the builders seem to have positioned heavier stones directly above naturally stronger support pillars, while lighter slabs occupy weaker sections. That kind of load management should require advanced architectural planning. Yet La Roche-aux-Fées predates Roman engineering by nearly 3 millennia. The transport of the stones remains one of the first major unsolved problems. Geological studies suggest several stones came from locations kilometers away. Moving blocks weighing 20–45 tons across muddy terrain without wheels, cranes, or iron tools would have been extraordinarily difficult. Experimental archaeology suggests that dragging a 30-ton stone across wet ground could require over 150 people working simultaneously using wooden rollers and rope systems. But there is another problem. No evidence of a nearby settlement large enough to support such a labour force has ever been found close to the monument. This has led some researchers to believe that megalithic construction in prehistoric Europe may have involved regional cooperation networks far more organised than previously assumed. Similar patterns appear at Stonehenge, where blue stones were transported over 200 kilometres, and at Carnac stones, where thousands of aligned stones suggest coordinated labour on a massive scale. But the greatest mystery of La Roche-aux-Fées is hidden in what engineers call its dry lock construction system. The monument contains no mortar whatsoever, no cement, no resin, no metal reinforcement, and yet the stones remain tightly interlocked after more than 4,000 years of exposure to Brittany's wet Atlantic climate. This is where the structure becomes deeply difficult to explain. Several contact points between the stones show extremely narrow gaps, despite the surfaces not being perfectly flat. Instead of relying on smooth-cut geometry like later Greek or Roman masonry, the builders appear to have exploited natural pressure balancing. Some archaeologists believe the stones were carefully selected and rotated to create complementary weight distributions, essentially allowing gravity itself to lock the structure together. This resembles principles later seen in Incan polygonal masonry at Sacsayhuaman, where massive stones fit so tightly that even modern blades cannot easily slide between them. But the Inca achieved this nearly 4,000 years later. At La Roche-aux-Fées, the builders accomplished stability using rough megalithic slabs with no evidence of advanced cutting tools. That creates a serious technological contradiction. Modern engineers studying ancient dry stone structures note that stability without mortar requires precise management of 3 factors: weight distribution, friction coefficient between surfaces, and center of mass alignment. If even one capstone was slightly misaligned, thousands of kilograms of downward force could eventually destabilize the corridor over centuries of erosion and seasonal ground movement. Yet the structure still stands. Laser scanning surveys have shown that several pillars lean inward at subtle angles, possibly intentionally. This may have created compressive force channels that strengthened the structure over time instead of weakening it. Similar inward force stabilization appears in Mycenaean Cyclopean walls and certain Andean stone structures, but those civilizations emerged much later. The possibility that Neolithic Europeans independently discovered primitive forms of force distribution engineering is now taken seriously by some researchers. Even stranger is the geological stability of the monument itself. Brittany's soil contains moisture-rich clay layers prone to gradual shifting. Over millennia, structures built on such terrain typically suffer uneven subsidence. Many smaller European dolmens collapse precisely because their foundations slowly destabilized. La Roche-aux-Fers somehow resisted that fate. Some engineers suspect the builders intentionally chose slightly flexible foundation zones, capable of absorbing tiny seasonal movements without fracturing the structure. Others believe the enormous weight of the monument compacted the soil over time into a more stable, load-bearing platform. But no definitive explanation exists. The astronomical alignment of the structure adds another layer to the mystery. During the winter solstice, sunlight penetrates deep into the passage at a highly specific angle. This phenomenon resembles alignments found at Newgrange, where sunlight illuminates an internal chamber during the solstice with extraordinary precision. To achieve this, Neolithic builders would have needed long-term solar observations across many years. The Earth's seasonal solar positions shift gradually along the horizon, meaning the alignment could not have been accidental. The corridor orientation suggests deliberate astronomical planning. What remains unknown is how prehistoric communities without writing systems preserved this observational knowledge across generations accurately enough to execute such projects. Some theories propose that megalithic monuments function not only as tombs, but as ceremonial calendars tied to agricultural cycles and ritual authority. Others suggest they may have served as territorial symbols, demonstrating control over labor, engineering, and sacred knowledge. Yet even those theories do not fully solve the engineering puzzle, because the monument survives in conditions that should have destroyed it long ago. The Atlantic climate of Western France produces constant humidity fluctuations, biological erosion, and repeated freeze-thaw cycles capable of cracking stone over centuries. Many medieval structures across Europe required continuous maintenance to survive these conditions. La Roche-aux-Fers had none, and still it endured. Some geologists argue that the builders intentionally selected stone types with unusually high resistance to moisture penetration and thermal stress. Others point toward the monument's layout itself. The slight gaps between some stones may actually help relieve pressure during seasonal expansion, preventing catastrophic cracking. If true, that would mean the builders understood not only weight distribution, but long-term environmental stress behavior in stone. Thousands of years before formal engineering science existed, do you think La Roche-aux-Fers was built using forgotten engineering knowledge? Or is there still something about ancient civilizations we completely misunderstand? Share your thoughts in the comments below. Ein Hemed sits inside the Judean hills west of Jerusalem, surrounded by dry limestone ridges where water should vanish quickly beneath fractured rock. Yet for nearly 1,000 years, this site maintained flowing springs, stable vegetation, cool air, and stone structures that survived repeated earthquakes in one of the most unstable regions of the Middle East. Archaeologists expected a small crusader roadside stop. Instead, they found evidence of hydraulic planning, climate manipulation, and engineering precision that still raises questions today. Modern archaeological interest in Ein Hemed intensified during the 20th century when surveys around Jerusalem began documenting Crusader-era structures hidden in the valleys west of the city. Excavations revealed vaulted halls, massive masonry walls, water channels, reservoirs, and unusually sophisticated drainage systems connected directly to nearby springs. At first, researchers classified the site as a minor Crusader way station, used by pilgrims travelling toward Jerusalem during the 12th century. But the deeper archaeologists studied the site, the stranger it became. The amount of engineering dedicated to water management appeared far too advanced for a small resting station. Some underground channels were carefully angled with gradients so precise that modern engineers later estimated the slope variations at only a few millimeters per meter, comparable to Roman aqueduct standards. The discovery transformed Ein Hemed from a forgotten ruin into one of the most puzzling hydraulic sites in the Judean hills. The greatest mystery surrounding Ein Hemed is not its walls, it is the environment itself. Even today, visitors entering the valley often experience a sudden temperature drop compared to the surrounding hills. The air becomes cooler, more humid, and noticeably greener despite the semi-arid climate of the region. In summer, temperatures around Jerusalem regularly exceed 30 degrees Celsius, while humidity remains relatively low. Yet inside the Ein Hemed Valley, the conditions feel dramatically different. Environmental researchers studying the site discovered that the arrangement of water channels, reservoirs, vegetation, and stone structures creates what modern scientists call a microclimate system. The placement of walls and pools appears to redirect airflow through shaded wet areas before the air enters living spaces. This naturally cools the environment without any mechanical technology. What makes the phenomenon difficult to explain is the precision involved. Computer simulations conducted on similar Middle Eastern passive cooling systems show that small errors in orientation can drastically reduce cooling efficiency. A wall angled incorrectly by only several degrees can disrupt airflow patterns entirely. Yet the layout at Ein Hemed consistently maximizes shade retention, moisture circulation, and evaporative cooling. Some researchers compare the effect to Persian windcatcher systems used centuries later in Iran, where towers directed air through underground water channels to cool buildings naturally. Others compare it to Nabatean environmental engineering at Petra, where water and architecture were combined to manipulate local climate conditions. But Ein Hemed differs in one crucial way. The cooling effect is embedded into the natural valley itself, rather than relying only on architectural structures. Satellite vegetation studies have shown that moisture retention in the valley remains significantly higher than in neighboring terrain. Geological surveys indicate that water flowing through porous carbonate rock beneath the site may interact with engineered surface channels to stabilize humidity levels. In other words, the builders may have understood how underground hydrology and surface airflow could work together as a single environmental system. The question is difficult to answer because medieval builders supposedly lacked modern thermodynamics, airflow modeling, or geological mapping tools. Yet the valley behaves almost like a deliberately engineered oasis. Some climatologists believe the builders learned through centuries of observation and experimentation. Others argue the system may preserve older Byzantine or Roman environmental knowledge lost elsewhere in the region. Either way, the level of environmental control achieved at Ein Hemed remains astonishing for the period. Water should have been the greatest limitation of the site. The Judean hills are dominated by fractured limestone formations that absorb and redirect groundwater unpredictably. Seasonal flow changes can rapidly dry out springs, especially in hot summers. Yet Ein Hemed maintained reliable water circulation through pools, channels, and storage systems for centuries. Hydrological studies suggest the builders intentionally placed channels along zones where subsurface rock retained higher moisture content. This helped stabilize water pressure naturally. Several researchers compare the engineering to Roman aqueduct systems such as Pont du Gard in France, where water gradients had to remain extremely precise across long distances. At Ein Hemed, however, the challenge was even harder because the terrain is irregular and mountainous rather than relatively open and linear. Modern reconstructions indicate that some channels maintained slopes below 1% while still preventing stagnation. If the gradient became too steep, erosion would damage the channels. If it became too flat, water flow would stop entirely. Achieving this balance without laser surveying equipment remains difficult even for modern restorations. Archaeologists also identified overflow diversion systems that prevented sudden seasonal flooding from damaging the main structures. These diversions appear intentionally integrated into the valley landscape itself, rather than added later. Some engineers argue the hydraulic planning at Ain Hemed demonstrates empirical knowledge far beyond what historians traditionally associate with Crusader frontier architecture. Ain Hemed lies relatively close to the Dead Sea Transform fault system, one of the most seismically active zones in the Middle East. Over the past 2,000 years, the region experienced numerous destructive earthquakes that damaged Jerusalem, Jericho, Tiberias, and many surrounding settlements. Yet major portions of Ain Hemed remain standing. The explanation may lie in the masonry itself. Unlike many medieval fortifications that depended heavily on rigid mortar bonding, several sections of Ain Hemed appear constructed using partially interlocking stone arrangements. Massive limestone blocks distribute weight unevenly across flexible contact points, rather than through completely rigid connections. Structural engineers studying ancient earthquake-resistant construction often compare this principle to Inca stonework at Machu Picchu and Sacsayhuaman. Those structures survived centuries of seismic activity because their stones could shift slightly during tremors before settling back into place. At Ain Hemed, certain wall joints are so narrow that inserting a thin metal blade between stones becomes nearly impossible. Yet the walls still display subtle flexibility under stress. Some researchers suggest Crusader builders may have absorbed local Levantine construction techniques inherited from Byzantine or even earlier Roman traditions. Others believe the builders intentionally adapted the structure after observing repeated earthquakes in the region. No definitive answer exists, but the survival rate of the site compared to neighbouring ruins remains difficult to ignore. Another mystery lies within the mortar itself. Laboratory analysis shows the material at Ain Hemed contains lime, mineral ash, and silica-rich particles capable of producing pozzolanic reactions. The same process that allowed ancient Roman concrete to survive for thousands of years. What makes this difficult to explain is that constant moisture normally destroys medieval mortar relatively quickly. Yet large parts of the hydraulic system at Ain Hemed remain intact after nearly 9 centuries. Microscopic studies even found mineral crystals continuing to grow over time, potentially making the material stronger. No surviving Crusader records describe such a formula. If the builders truly combined Roman, Byzantine, and Islamic construction knowledge, Ain Hemed may represent a technological fusion that historians still do not fully understand. Do you think Ain Hemed was really just a pilgrim station? Or could it have been part of a much larger hidden engineering system? Share your thoughts in the comments below. In the mountains of Cumbria, northwestern England, Hardknot Roman Fort stands in one of the most hostile locations ever chosen by the Roman Empire. Surrounded by freezing winds, dense fog, and steep volcanic terrain, the fortress looks less like a military outpost and more like a failed experiment abandoned by history. Yet nearly 2,000 years later, parts of its roads, walls, drainage systems, and heating technology still survive. The deeper archaeologists investigate Hardknot, the more one question emerges. Why would Rome build such an advanced fortress in a place that seemed almost impossible to sustain? The fort was first identified through antiquarian surveys in the 18th century, but serious archaeological work accelerated during the 19th and 20th centuries as researchers connected the site to the Roman road network of Britannia. Excavations revealed barracks, defensive gates, command buildings, and one of the most unusual Roman bathhouses ever discovered in Britain. Inscriptions suggest the fort was constructed around 120 CE during the reign of Emperor Hadrian, the same era that produced Hadrian's Wall. But unlike Hadrian's Wall, which defended a frontier, Hardknott appeared isolated deep inside mountainous terrain, with no major city nearby. That contradiction became the beginning of its mystery. The first unexplained anomaly is the road itself. Hardknott Pass remains one of the steepest roads in Britain even today, with gradients approaching 30% in certain sections. Modern vehicles struggle on the climb, especially during rain or winter ice. Yet Roman engineers managed to carve a military road directly across this terrain nearly 2 millennia ago. Archaeologists discovered that the road was not a simple dirt trail. It consisted of multiple engineered layers, compacted stone foundations, gravel compression surfaces, and drainage channels designed to redirect water away from the roadway. This layered construction resembles principles still used in modern civil engineering. The mystery is logistical. Thousands of tons of material would have been required to stabilize the route, but the surrounding terrain offers limited access for transport animals or wheeled carts. Historians estimate Roman military engineering units could move roughly 1 to 1.5 tons per cart under favorable conditions. On gradients approaching Hardknott slopes, that capacity would likely collapse dramatically. Even today, building a stable mountain road in similar terrain requires heavy machinery, retaining walls, and advanced geological analysis. Rome somehow achieved a functioning military highway with hand tools, manpower, and surveying instruments. Even stranger is the geometric precision of the fort itself. From aerial analysis, Hardknott forms a remarkably symmetrical square layout despite sitting on uneven volcanic ground. Roman surveyors used tools like the groma for alignment and the chorobates for leveling, but maintaining near-perfect military geometry on a sloped mountainside remains difficult even with modern equipment. Researchers studying Roman military camps have noted that Hardknott's internal alignment appears unusually optimized for visibility across surrounding valleys. Some historians believe the fort may have functioned partly as a signaling station, using smoke or fire communication with nearby outposts across Cumbria. The orientation of its gates and towers seems designed not merely for defense, but for long-distance observation through narrow valley corridors. That level of environmental integration suggests Roman military engineers possessed a far deeper understanding of terrain optimization than commonly assumed. But the greatest mystery of Hardknott lies inside its bathhouse. At first glance, a Roman bath complex in northern England may not sound unusual. Similar bathhouses existed throughout the empire, from North Africa to the Rhine frontier. The difference is environmental reality. Cumbria experiences heavy rainfall, freezing temperatures, high humidity, and violent Atlantic winds blowing inland from the Irish Sea. Maintaining a heated structure under those conditions should have consumed enormous amounts of fuel. Yet archaeological evidence suggests the bathhouse operated effectively for decades. The bathhouse used the Roman hypocaust system, one of the most sophisticated heating technologies of the ancient world. Beneath the floor stood rows of small pillars supporting suspended stone tiles. Furnaces generated hot air which circulated under the floor and through hollow wall flues, warming the entire structure. In theory, the system worked like a primitive form of central heating. But theory and reality are very different in mountain climates. Heat loss increases dramatically in wet and windy environments. Modern thermodynamic studies show that humid cold air strips heat faster than dry cold air because moisture accelerates conductive heat transfer. In a place like Hardknott, sustaining interior temperatures comfortable for bathing would have required continuous fuel input and highly efficient insulation. This is where the mystery deepens. Excavations indicate that Hardknot's bathhouse walls are unusually thick compared to some lower-altitude Roman bathhouses in southern Britain. Researchers also found evidence that the structure was positioned strategically behind terrain features that partially blocked prevailing winds. Some engineers believe the Romans may have unintentionally created a primitive thermal efficiency system through orientation and wall mass. Thick masonry absorbs heat slowly but retains it for long periods, similar to passive thermal regulation techniques used in modern eco-architecture. In essence, the bathhouse may have functioned partly like a thermal battery. Comparisons with other Roman sites make Hardknot even more fascinating. Bathhouses in warmer provinces like Italy or North Africa benefited from relatively stable climates and abundant fuel sources. Hardknot had neither. Forest resources in mountainous Cumbria were limited, and transporting firewood uphill would have been extremely expensive in labour. A Roman soldier stationed there may have required several kilograms of wood daily just to support heating operations collectively across the fort. Some historians argue the fuel burden alone should have made long-term operation impractical, yet the system endured. That suggests Roman logistics and environmental adaptation were far more advanced than traditional depictions of ancient engineering imply. Another unexplained feature involves water management. Roman bathhouses required reliable water flow not only for bathing but also for heating stability. Water channels discovered near Hardknot indicate careful hydraulic planning despite the unstable mountain environment. Roman engineers appear to have redirected natural water sources while simultaneously protecting structures from flooding caused by heavy rainfall. The drainage systems around the fort remained surprisingly effective even after centuries of erosion. Modern archaeologists comparing Roman drainage with early medieval construction in Britain often note that Roman systems were vastly superior in durability and efficiency. Then comes the question of why the fort was abandoned. Archaeological layers suggest Hardknot was occupied, partially abandoned, and later reoccupied. This cycle confuses historians. Rome rarely invested heavily in mountain fortresses without strategic necessity. Some theories blame climate deterioration during the later Roman occupation of Britain. Others suggest tribal resistance from local populations made supply routes too dangerous. There are also indications that maintaining the road network across the mountains became increasingly unsustainable as imperial resources weakened during the 3rd century CE. But none of these explanations fully account for the scale of investment originally placed into the site. What do you think was the real purpose of Hardknot Roman fort? A military outpost, a hidden signalling station, or proof that Roman engineering was far more advanced than we realize? Share your thoughts in the comments below. In the arid plains of central Jordan, near the edge of the ancient King's Highway, Rasas looks like little more than a field of clapstone walls. But beneath the desert dust lies one of the strangest technological mysteries of the Byzantine world, a forgotten city whose mosaics survived over 13 centuries of brutal desert climate, whose water systems functioned in near-impossible conditions, and whose construction techniques still confuse engineers and archaeologists today. The site was first systematically documented in the 19th century by European explorers traveling across Ottoman-controlled Jordan. Later excavations revealed something unexpected. Rasas was not a small desert outpost, but a massive fortified settlement covering nearly 1 square kilometre, containing military structures, churches, underground reservoirs, workshops, and one of the largest Byzantine mosaic floors ever discovered in the Middle East. Archaeologists eventually identified traces from multiple civilizations layered together: Roman, Byzantine, and early Islamic Umayyad occupation, spanning nearly 1,000 years of continuous use. What shocked researchers most was not simply the size of the settlement. but how advanced its engineering appeared for a city built in one of the harshest semi-arid environments in the region. Annual rainfall around the area averages barely 100 to 200 millimeters per year. Summer surface temperatures can exceed 40 degrees Celsius, while winter nights can approach freezing. In climates like this, ancient masonry usually erodes rapidly from salt crystallization, thermal expansion, and sand abrasion. Yet parts of Amarasas remain astonishingly intact. One of the greatest mysteries surrounds the enormous mosaic floor inside the Church of St. Stephen, built around 785 AD. The mosaic covers hundreds of square meters and depicts cities across the Levant, including Jerusalem, Gaza, Nablus, and Alexandria. The geometric precision is extraordinary. Thousands of tesserae, tiny stone cubes often only a few millimeters wide, were placed with almost machine-like consistency. Modern restorers studying the floor noticed that many alignment lines deviate by less than a few millimeters across large distances. In several sections, the symmetry remains intact despite over 12 centuries of earthquakes, soil movement, and thermal stress. Researchers compare the floor to mosaics from other Byzantine sites such as Madaba and Jerash. While those locations also contain sophisticated artwork, Amarasas displays unusually low distortion for a structure exposed to open desert conditions for centuries. Some specialists believe ancient builders may have used advanced grid systems, tension cords, or mathematical layout methods similar to techniques later used in Renaissance architecture. Others suggest the builders possessed highly standardized production methods for stone cutting and placement that exceeded normal expectations for frontier settlements. Even stranger is the survival of the pigments themselves. Mineral analysis revealed traces of iron oxides, copper-based compounds, carbon black, and locally sourced limestone materials that somehow retained color stability despite centuries of ultraviolet exposure and temperature fluctuation. In many ancient desert sites, pigments fade rapidly because repeated heating and cooling fractures the microscopic structure of the stone surface. At Amarasas, several sections still preserve recognizable shades after more than 1,300 years. Another unexplained structure stands isolated beyond the main settlement, the Stylite Tower. Rising roughly 15 meters above the surrounding plain, the tower was likely used by ascetic monks known as stylites, who lived atop pillars for years as acts of religious devotion. But engineers studying the tower noticed structural characteristics that seem unusually sophisticated for a remote Byzantine desert settlement. The tower's height-to-base ratio approaches instability thresholds even by medieval masonry standards. Yet it survived repeated regional earthquakes that damaged far newer structures nearby. Stone blocks were fitted with remarkable uniformity, distributing vertical load efficiently while minimizing lateral weakness from desert winds. Researchers believe the builders understood principles of weight transfer and vibration dampening far better than previously assumed. Some even proposed the tower may have doubled as a navigation marker or signaling point visible to caravans crossing the desert. Beneath the city lies another major mystery: water. Archaeologists uncovered underground cisterns, channels, settling basins, and waterproof reservoirs capable of storing massive quantities of seasonal rainfall. In a region lacking major rivers, sustaining a large population should have been nearly impossible. Yet Amarasas functioned for centuries. The hydraulic system appears engineered with astonishing precision. Several channels maintain carefully calculated gradients that slow water movement just enough to reduce erosion while maximizing storage efficiency. Certain reservoir walls contain mineralized coatings that remain partially waterproof even today. Laboratory analysis identified mixtures of lime mortar, volcanic ash, crushed ceramics, and organic additives whose exact formula remains uncertain. The durability of these materials has drawn comparisons to Roman marine concrete found at ancient ports like Caesarea and Pozzuoli. In those structures, volcanic compounds reacted chemically with seawater to strengthen over time through mineral crystallization. At Umarasas, researchers discovered evidence suggesting similar long-term mineral reactions may have occurred inside the mortar, allowing microscopic cracks to self-seal gradually across centuries. This leads directly to one of the most important and least understood mysteries of the entire site: the survival of its construction materials through over 1,300 years of desert climate. Most ancient plaster, mortar, and surface coatings exposed to desert environments eventually collapse under repeated thermal stress. During daytime, stone surfaces expand under extreme heat. At night, rapid cooling contracts them again. This cycle creates internal fractures that slowly destroy masonry from within. Salt carried by wind or groundwater worsens the damage by crystallizing inside microscopic pores. Yet many structures at Umarasas resist this destruction far better than expected. Some mortar layers remain tightly bonded to stone after more than a millennium outdoors. Sections of plaster still adhere to walls despite constant exposure to wind erosion. In several mosaic foundations, the bonding substrate retains structural cohesion that modern cement mixtures often lose within decades under similar conditions. Microscopic studies revealed unusually dense crystalline structures inside portions of the mortar. Certain samples showed evidence of delayed mineral growth, meaning the material may have continued chemically strengthening long after construction. Researchers also found traces of ceramic particles finely crushed into the mixture, possibly functioning similarly to pozzolanic additives used in Roman concrete technology. Comparisons with modern Portland cement produced disturbing results. Under simulated desert weathering tests, some reconstructed ancient mixtures demonstrated slower crack propagation and better moisture regulation than certain contemporary building materials. This raises an uncomfortable possibility. Some ancient construction knowledge may not merely equal modern techniques under desert conditions, it may outperform them. Another mystery involves city planning itself. Satellite imaging reveals that Umarasas was organized with surprising precision. Streets align along controlled axes despite uneven terrain. Religious structures appear distributed according to intentional spatial hierarchy. Certain buildings may align with seasonal solar positions, particularly during equinox sunrise angles. Some archaeologists believe Byzantine surveyors at the site employed astronomical observations for orientation and planning. Others argue the layout reflects inherited Roman military engineering traditions adapted to desert geography. Either way, the settlement demonstrates a level of organizational control rarely associated with remote frontier communities. Then, suddenly, the city vanished. Despite evidence of long occupation, Umarasas appears to have been abandoned gradually between the 8th and 9th centuries. There are few signs of catastrophic destruction. Many mosaics remained untouched. Some structures appear simply left behind. Historians debate whether climate shifts, collapsing trade routes, earthquakes, political instability, or water failure triggered the decline. No single explanation fully accounts for the disappearance. Do you think the builders of Umarasas possess construction knowledge that modern science still cannot fully explain? Share your thoughts in the comments below. In the Negev desert of southern Israel, Elusa once supported a massive population in a region receiving barely 70 to 100 millimeters of rainfall per year. 2,000 years ago, while much of the ancient world struggled against arid climates, Elusa transformed one of the harshest deserts on Earth into a functioning agricultural and trade metropolis. The deeper archaeologists dig into the ruins, the more impossible the city begins to look. The ruins of Elusa, also known as Haluza, were identified in the 19th century by explorers traveling ancient caravan paths across the Negev. At first, researchers believed the site was simply another abandoned Nabatean settlement connected to Petra and Gaza. But aerial photography, satellite imaging, and modern excavations revealed something far larger: an advanced urban centre with sophisticated water engineering, agricultural infrastructure, warehouses, churches, bathhouses, and road systems spread across the desert. UNESCO later included the site within the incense route World Heritage Corridor because of its importance in ancient long-distance trade. The greatest mystery surrounding Alusa is not its temples or architecture. It is the fact that the city should never have been able to feed itself. Modern climate data shows that the Negev Desert is one of the driest inhabited regions in the Middle East. Annual evaporation rates can exceed 2,000 millimeters, more than 20 times the yearly rainfall. In such conditions, even modern agriculture requires pipelines, pumps, desalination systems, and computerized irrigation. Yet nearly 2,000 years ago, the inhabitants of Alusa managed to support vineyards, grain production, orchards, and caravan animals on a massive scale. Satellite surveys around Alusa reveal thousands of ancient agricultural plots carved into dry valleys. Archaeologists discovered low stone terraces, flood diversion walls, runoff channels, and sediment traps stretching for kilometers across barren land. These systems were not random. They were engineered with remarkable precision to capture seasonal flash floods that occurred only a few times each year. This is where the mystery becomes difficult to explain. Flash floods in deserts are violent and unpredictable. Water can move at speeds exceeding several meters per second, carrying rocks, mud, and debris capable of destroying poorly designed structures almost instantly. Modern hydrologists studying Nabatean systems found that many channels around Alusa maintained slopes carefully balanced between erosion and retention. If the gradient had been slightly steeper, the channels would have collapsed, slightly flatter, and water would stagnate or fail to reach agricultural zones. Yet the system worked. Researchers comparing Nabatean flood harvesting techniques with modern dryland farming have noted efficiencies surprisingly close to modern runoff agriculture. Some reconstructed fields demonstrated moisture retention lasting weeks after a single flood event. This suggests the inhabitants understood soil absorption, sediment control, and seasonal water behavior at a level far beyond what historians once assumed for ancient desert societies. Even more mysterious is the scale. Archaeological evidence suggests that the agricultural zone surrounding Alusa may have covered thousands of hectares. Some estimates indicate production levels large enough not only to sustain the city itself, but also to export wine and crops northward toward Mediterranean markets. Amphora fragments discovered across the Negev indicate large-scale storage and transport operations. Ancient texts even mention Gaza wine, a famous export linked to settlements like Alusa during the Byzantine period. The question is unavoidable. How did a civilization without satellites, pumps, concrete dams, or digital measurements engineer a desert-wide agricultural network capable of surviving for centuries? Some scientists believe the Nabateans possessed generations of accumulated environmental knowledge so advanced that it functioned almost like primitive climate engineering. Others argue that regional climate conditions may have been slightly wetter during antiquity, although sediment core data suggests the difference was probably too small to fully explain Alusa's productivity. In many ways, the agricultural systems of Alusa resemble modern sustainability concepts more than ancient farming. Instead of forcing water into the desert, the city harvested the desert itself. The agricultural systems depended on another technological mystery: water control. Excavations uncovered underground cisterns, stone reservoirs, diversion dams, and long-distance runoff channels surrounding the city. Some storage systems were capable of preserving water for extended periods despite extreme heat. Several reservoirs were coated with mineral-rich plaster mixtures that reduced leakage and resisted erosion. This alone is impressive. But what confuses engineers is the precision. Modern desert infrastructure relies heavily on surveying instruments and elevation analysis. Yet Nabatean builders somehow calculated water flow across uneven terrain, using only manual methods. Several surviving channels maintain remarkably stable inclines over long distances. Researchers using drone mapping found evidence that the system directed water toward different agricultural sectors depending on flood intensity. In effect, the city may have operated a form of analog hydraulic management centuries before modern hydrology existed. The sophistication becomes even clearer when compared with nearby civilizations. Many Roman settlements in arid regions relied heavily on aqueducts connected to permanent springs. Elusa could not. There were no large rivers nearby. The city survived almost entirely through rainfall harvesting and runoff control. That changes the historical picture completely. Elusa was not merely surviving the desert, it was actively engineering it. Another unresolved mystery involves the city's building materials. The Negev desert experiences severe thermal stress. Summer daytime temperatures can exceed 40 degrees Celsius, while nighttime temperatures drop dramatically. Constant wind erosion and sand abrasion rapidly destroy exposed surfaces. Many modern materials deteriorate under such conditions within decades, yet portions of Elusa's foundations, walls, reservoirs and road systems survived for nearly 2 millennia. Laboratory analysis of Nabatean plaster and mortar found unusual combinations of lime, ash, desert minerals and microscopic organic components. Some researchers believe the mixture improved flexibility and reduced cracking caused by thermal expansion. Others suspect the builders intentionally modified local materials to improve water resistance. This mirrors other ancient material mysteries seen in Roman marine concrete or certain Persian desert fortifications, where ancient formulas displayed durability rivaling or exceeding some modern equivalents. What makes Elusa particularly fascinating is that these materials were used not in a temperate climate, but in one of the harshest environments imaginable. Elusa was positioned along the incense route, the massive trade network connecting Arabia with the Mediterranean world. Frankincense, myrrh, spices, textiles, and luxury goods passed through the Negev for centuries, but maintaining desert trade on that scale required extraordinary logistics. Caravans containing hundreds of camels consumed enormous quantities of water. Archaeologists discovered roadside stations, storage compounds, and structures believed to function as supply hubs surrounding Elusa. Some routes were positioned with striking geographic efficiency, minimizing exposure to dangerous terrain while maximizing access to seasonal runoff areas. The organization resembles a primitive form of modern supply chain engineering. Without reliable infrastructure, a single failed water station could destroy an entire caravan operation. Yet Elusa remained active for centuries, suggesting the Nabateans developed an exceptionally stable logistical system in an environment where small mistakes often meant death. Perhaps the strangest mystery is how rapidly the city disappeared. During the Byzantine era, Elusa flourished as one of the largest settlements in the Negev. Then, within a relatively short historical period, it declined dramatically. Archaeologists found no clear evidence of catastrophic warfare or total destruction. Many hydraulic systems appear to have remained functional late into the city's existence. Several theories attempt to explain the collapse. Some historians point to changes in global trade routes after the rise of maritime commerce. Others suggest prolonged drought cycles destabilized agricultural production. Climate reconstructions indicate that even minor reductions in rainfall could have devastated a system dependent on precise runoff timing. If true, Elusa may represent one of history's earliest examples of environmental economic collapse. A highly optimized civilization destroyed not by invasion, but by fragile dependence on complex infrastructure. Do you think Elusa was simply an advanced desert civilization? Or evidence that Ancient societies understood environmental engineering far better than we do today? Share your thoughts in the comments below. In the heart of Rome, buried beneath parks, roads, and later imperial buildings, lies a structure many archaeologists consider one of the strangest engineering experiments of the ancient world: Domus Aurea. Built by Emperor Nero after the Great Fire of 64 AD, the Golden House was not simply a palace. It was a machine of architecture, psychology, and technology so advanced that parts of it still remain unexplained nearly 2,000 years later. The ruins were rediscovered accidentally during the late 15th century when Renaissance explorers fell through cracks in the ground into buried chambers covered in ancient paintings. Artists like Raphael descended with ropes and torches, believing they had entered underground caves. Instead, they had entered the remains of Nero's lost mega-palace, a structure once covering nearly 200 acres, stretching across parts of the Palatine, Oppian, and Caelian hills. But the deeper archaeologists investigated, the stranger Domus Aurea became. The greatest mystery surrounds a room described by Roman historian Suetonius. According to his writings, Nero possessed a dining chamber with a rotating ceiling that moved continuously like the heavens. At first glance, the statement sounds exaggerated, almost mythological. Yet many historians now believe the mechanism may have been real. If true, it would mean Roman engineers in the 1st century AD created a rotating architectural system more than 1,800 years before modern mechanical domes. The engineering problems alone are staggering. A rotating ceiling made from stone, timber, plaster, and bronze would have weighed several tons. To move continuously, the structure would require load distribution, rotational balance, friction reduction, and some form of constant power source. Even modern rotating restaurants use electric motors and steel bearings to maintain stability. Roman engineers had neither. Some archaeologists suspect the mechanism relied on water power. Others believe hidden slave-powered capstans beneath the floor slowly turn the structure through a vertical axle. A more radical theory proposes that lubricated bronze rollers functioned as primitive bearings, but no surviving mechanism has ever been found. What makes the mystery even more disturbing is timing. Domus Aurea predates the Pantheon's famous dome by decades. The Pantheon, completed under Hadrian around 126 AD, remains the largest unreinforced concrete dome on Earth, nearly 1,900 years later, spanning about 43.3 meters. Many engineers believe the experiments conducted inside Nero's palace may have directly influenced later Roman dome technology. The ceiling chamber may have been a prototype, not merely decoration, but an early engineering laboratory, and Domus Aurea was filled with such impossible ideas. Roman builders used a specialized form of concrete known as opus caementicium, but tests conducted on materials from the palace reveal unusually lightweight volcanic aggregates. Engineers discovered that upper structural sections used lighter mixtures than lower supports, reducing downward stress on vaults and ceilings. This resembles modern gradient density concrete engineering, where material density changes depending on structural load. The Romans should not have understood this principle with such precision, yet the evidence suggests they did. Volcanic pozzolana ash mixed with lime created chemical reactions that allowed Roman concrete to survive moisture far better than many modern mixtures. In some samples, mineral crystals formed over centuries inside microscopic cracks, effectively self-healing portions of the structure. Similar reactions were identified in Roman harbor concrete studied by researchers from the University of Utah and geological teams analyzing ancient marine structures. Compared to many modern reinforced concrete buildings, which often begin degrading within 50 to 100 years due to steel corrosion, parts of Domus Aurea have survived nearly 20 centuries underground. But the palace was not only structurally advanced, it was psychologically engineered. Ancient writers described rooms covered in gold leaf, polished marble, gemstones, ivory, and reflective pools. Torchlight bouncing across curved walls would create shifting waves of light throughout the interior. Modern architectural psychologists compare the effect to immersive environmental manipulation, spaces designed to overwhelm human perception. Some corridors appear intentionally angled to redirect natural and artificial light deeper into the palace. Even more mysterious are chambers with unusual acoustic properties. In several rooms, echoes amplify selectively depending on position, suggesting Roman architects may have intentionally manipulated sound resonance. The same civilization that perfected amphitheatre acoustics may also have experimented with psychological architecture inside Nero's residence. And then there is the climate system. Rome's summers are brutally hot, often exceeding 35 degrees Celsius. Yet parts of Domus Aurea maintain relatively stable internal temperatures even today. Archaeologists uncovered hidden ventilation shafts, hollow wall spaces, underground corridors, and interior water features that likely function together as a passive cooling system. Cold air from subterranean chambers may have been drawn upward, while warm air escaped through higher vents, creating natural circulation. The principle resembles modern passive climate engineering used in sustainable architecture. Persian wind catchers and Middle Eastern passive cooling towers are often celebrated as ancient environmental engineering masterpieces. Yet Domus Aurea may represent a Roman variation of the same concept, integrated directly into elite imperial architecture during the 1st century AD. The speed of construction makes this even harder to explain. After the Great Fire, Nero reportedly ordered vast sections of Rome cleared for his palace. Ancient sources claim thousands of workers labored continuously, completing major sections within only a few years. Building a mega complex with artificial lakes, vaulted halls, rotating mechanisms, climate systems, and experimental concrete technology in such a short time would challenge even modern logistics. Some historians believe Domus Aurea consumed so many resources that it intensified political hatred toward Nero himself. After Nero's death in 68 AD, later emperors attempted to erase the palace from history. Massive portions were filled with earth and buried intentionally. Structures such as the Baths of Trajan were constructed directly above the complex. Ironically, this destruction preserved many interiors by sealing them away from weather and sunlight. That preservation created another mystery: the paintings. When Renaissance artists entered the buried chambers, they discovered vivid frescoes that still retained remarkable colour after nearly 1,400 years underground. The pigments resisted moisture, mould and decay with unusual effectiveness. These underground grottos inspired the grotesque art style that spread across Renaissance Europe. Even today, conservators struggle to fully reproduce the durability of some Roman pigments and plaster techniques used inside the palace. And beneath everything lies the most unsettling possibility of all. Domus Aurea may not have been a palace in the traditional sense. It may have been an imperial demonstration project, a place where Roman architects tested technologies too ambitious, expensive, or experimental for ordinary construction. Rotating ceilings, lightweight self-preserving concrete, passive environmental control, psychological light manipulation, advanced vault engineering, acoustic experimentation, massive dome prototypes. Nearly every major architectural breakthrough associated with later Roman engineering appears here in an earlier, more experimental form. Do you think Domus Aurea was simply a luxurious palace, or a lost experimental laboratory of ancient Roman technology? Share your theory in the comments below.